Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and we are at the 149th Global Star Party with the theme of Trails of Time. This theme came about because of the Eta Aquarid, the Eta Aquarid meteor showers are occurring right now, and these are leftovers from Halley's Comet. And I certainly remember Halley's Comet back in the 80s. It is one of the things that kind of propelled me into becoming an amateur astronomer. I was in my young 20s at the time. It was a very, very exciting time and amazing to see something that had come around since antiquity, actually before even then, but recorded since antiquity. Um, so it made me think about how time and astronomy are intertwined in so many ways. Tonight we will have a number of great speakers, including Chuck Allen, who'll be coming on next, Ron Breacher, and Steve Edberg, just to name a few. Steve was one of my inspirations. He was a mentor and really encouraged me to get deep into the community of amateur astronomy because Steve was a JPL scientist on
Oh,
planetary missions, but was very involved with amateur astronomy as well. Um, but let me go ahead and bring on my co-host, David Levy. David, it's good to see you on. I was expecting maybe you might be on a little bit later, but that's very cool. Hold on for just a second. Here
well,
we
I
go.
rushed and hurried
Bring
and broke all
myself
the
on.
speed
Yeah.
limits, went through red lights, drove on the wrong side of the street, passed a couple of ambulances and fire trucks, and here I am. It's good to see
Eh,
Steve Adberg here. It's been a while since I've
Yes,
seen
sir.
you, and I heard that you didn't get the best of luck at the eclipse, and perhaps you might be able to share that with us when it's your turn. Anyway, my poetic quotation today is going to be a little limerick, just a limerick called Relativity. And Relativity, it first apparently appeared, I think, in Punch magazine in the 1920s. But I found it when it was published in the Journal of the Royal Astronomical Society of Canada in the late 1960s. And here it goes. There once was a lady named Bright, whose speed was far faster than light. She set out one day in a relative way and returned home the previous night. And now back to you, Scotty, and
I
thank you for
love that.
being patient.
How did she return home the previous night?
Relativity, going backwards, I
Relativity. It's
guess.
all relative. That's right. No, it's great.
My mom had a joke about relativity that apparently time always slows down when you spend it with your relatives.
Hmm.
But I think some of these jokes might have come from Einstein himself, because he was a good person to mock some of his own ideas sometimes with humor.
No, that's great. That's
Scott,
great.
after the 1998 Leonids, I left, coming home, we left Tokyo Narita at early afternoon, and I arrived home well, uh, the same date in the morning in Los Angeles. It happens.
That can happen. That's right. That's right.
These things can happen.
Right.
Um, anyway, it's good to see everybody today.
Yes. Okay. We are going, David, we're going to go to Chuck Allen, who is obviously with us from the Astronomical League. He's been on several times, many times now. And Chuck always has a good topic. This time it's about unusual galaxies. And it's nice. You're kind of taking David Eicher's spot here a little bit on the unusual aspects of the universe, or at least with galaxies. David Eicher's on his way to Starmus right now, and that's going to be getting underway on the 12th. And so we're just a few days away from that. But we're going to be holding down the fort here with Global Star Party. So I'm going to.
And let me just add my welcome to Chuck. I just saw you a little while ago at Neve. Neve didn't work out too well for me, it turns out, because I caught COVID there. But the COVID is gone. It's now negative. All that I have left is
Already?
bronchitis. Yeah, it's now negative. I was tested on Sunday,
Mm,
and it came back negative. And
that's great.
except for the bronchitis, which I usually get now with a cold, everything's gone. And I'm happy as a clam.
Well, David, you're quite a fighter over there. I'm happy to hear that prognosis. Um, I'm in transit. I'll be home soon after I pick up my meal because I think I'm on in a few after a few speakers, so I'll be getting there. But had to say something to you, my friend. Glad you glad your immune system is working well as it should. And now I got to
Well,
go
it's
pay for my
trying.
meal.
It's trying.
Yep, he's a strong guy. So, well, Chuck, we're going to give you the stage. I'm excited. Both David and I are very excited about the upcoming Alcon event that you're going to be managing and hosting. And for those of you who are not familiar with the Astronomical League or the Astronomical League Convention, that's an event that's held each year by the world's largest federation of astronomical clubs. They have hundreds of clubs in their membership and tens of thousands of members. And it's a privilege and an honor to be associated with these guys. And if you go to the Astronomical League Convention, you're going to make a lot of new friends if you've never been before. And if you have been there before, you're going to meet a lot of your old friends. So, this particular one is special because, to me anyways, because we're going to go to the Linda Hall Library, which is a place where many incredible manuscripts of from amazing astronomers throughout history, even up into the modern day, with like some of David Levy's observations are kept there, and his first telescope's kept there. So it's going to be special. Let me just say that. So I'll turn this over to you, Chuck. Thank you so
Hey,
much, man.
thank you very much. Is my audio okay still?
It's beautiful.
Okay, fantastic. Good evening, everyone. Stephen, it's been a long time. You don't remember me, but I met you about 25 years ago once at a meeting, and it's great to see you here. And David, of course, you are now privileged to be the fourth person in the last year who's gotten COVID the day after I've seen them in person. I'm beginning to feel like Typhoid Mary here. So I'm glad you're okay.
So
Yeah.
Chuck, I don't want you to feel bad if I don't run up to you and give you a hug. Just saying.
I have been in 35 states, about 50,000 miles in road trips in the last, I think, 4 years. And I've been in large crowds all over the country, and I've never gotten COVID. I don't understand it. It's not
Wow.
like I've tried to avoid it at all.
Yeah.
So
Yeah.
incredible.
Yeah, knock on wood. I've kind of
Yeah.
You
had
may
a
be
similar
naturally
situation.
immune.
Yes,
So that's great.
knock
Yeah.
on wood. Okay. Let me share screen here. And let's see which one. That's the one. Okay, it should be visible to
Perfect.
everyone. Okay,
Looks good.
let me go back. This is a promotional for our convention in Kansas City on July 17th through 20th. And as Scott mentioned, we will be going to the Linda Hall Library and Powell Observatory as well, with their 30-inch reflector there, which is quite something to see. They're building a new observatory, by the way, further south to get a little further away from city lights. Kansas City is an exciting town, lots to do there. And we hope you'll join us there. And next year, we'll also be at Bryce Canyon. And for the 600 people who attended our convention in Bryce Canyon back in, I think, 2011, they'll all be back because the skies out there are just phenomenal. So keep a lookout for that. What I want to talk about tonight are just some unusual galaxies. So this is kind of easy listening. And we're just going to look at a couple different kind of odd ducks out there. The first is NGC 2787 in Ursa Major. This is what's called a lenticular galaxy. It's kind of a spiral that's morphing into an elliptical. Its bulge to disk ratio is very high. If you look at the overall picture here, you see what looks like a large elliptical, but they're telltale signs of a disk embedded in it. There are no spiral arms in this, as you can see. It's mostly older stars with very little star production going on. And that term lenticular will come up again here in a few minutes. Here we have what Guinness Book of World Records regards as the largest galaxy measured in stellar extent. This is IC 1101 in Virgo. It's a little more than 1.1 billion light years away. Very easy to observe, magnitude 13. It's a supergiant lenticular galaxy as well, and has a diameter of 550,000 light years. Compare that to the Milky Way. It's about 5 times bigger in diameter. The number of stars in this galaxy is estimated at 100 trillion stars. Wow. And it has a supermassive black hole at its core with a mass of 100 billion solar masses. So this is a giant in every respect. It's also a very yellow galaxy. It's a very old galaxy, metal rich, lots of older stars, red giants. And there's a cool little galaxy down here at the bottom called Leda 5057632. That's one of the most perfect edge-on I've ever seen. It's really spectacular. But we might have some larger candidates out there. This is ESO 38376 in Centaurus, and it is about 200 million light years away, and it has a diameter of 1.76 million light years, much larger than IC 1101, if indeed its stellar extent measures that. That's somewhat controversial at the moment, but if it holds, it would be about 3.5 times bigger than IC 1101, and about 20 times bigger than the Milky Way. But there may be an even larger candidate, and that is Leda 088678. Pardon for the lack of popular names here, they don't have them. This is in Virgo and has a diameter of over 3 million light years estimated. And this would be the largest known galaxy by stellar extent if, in fact, the data concerning this galaxy's distance proves to be correct. But there's one more galaxy that may be regarded as even bigger if you include the jets and lobes produced by the supermassive black hole at its core. And that's called Alcyonus in Lynx. And if you measure the distance from the lobes and jets, the lobes at the end of the jets, it has a length of 16 million light years. That's about 160 times the diameter of the Milky Way. And so, at least in that respect, it's the largest known structure of galactic origin, if not stellar extent. Well, then we go to NGC 6872 in Pavo. This is the Condor galaxy. It is the largest known spiral galaxy in existence. From tip to tip, it's about 717,000 light years, making it the largest. And note the extensive star formation going on in this northeast arm up here. And that's because it's interacting with this galaxy right here in the background, which is IC 4970, a little lenticular galaxy. And the gravitational effects are compressing gas and causing a lot of star formation in this region of the galaxy. Now, here we have a galaxy with an even more attractive name. I'm not even going to read it all. I'll just call it WISE. It's in Aquarius, and it's 12.5 billion light years of light travel time away. So we're looking at this virtually all the way across the observable universe, or at least most of it. Today, it actually lies at a distance of 25 billion light years. And it's a fairly small, about 30,000 light years in diameter. But here's an artist's conception of what's going on at this galaxy. And what you have is a central galaxy that's actually siphoning material off of 3 other galaxies at once. Talk about a cannibal. And part of the reason for this is that the center of this galaxy, there's a center, at the center, there's a supermassive black hole and quasar, actually, very active, that's pulling in this material. It has 10 billion solar masses, and it's the brightest known galaxy in the universe presently. It has 10,000 times the energy output of the Milky Way by comparison. And here we have just a really beautiful galaxy. It's called the Jellyfish Galaxy. It's in Triangulum Australis. It is ESO 137001. It's 220 million light years away, and it shouldn't be a mystery why it's called the jellyfish. It's about the same size as the Milky Way and the same type of SBC barred spiral galaxy that the Milky Way is. But it has tails of gas and dust that stream off from one side of this galaxy. The cause of this is still a mystery. And part of the mystery is you can see that those stars are blue. They're young, which means they're recently formed. And astronomers have not been able to figure out how stars can form in these streams of gas because the gas is too hot. Now, you may think, well, it has to be hot in order to fuse to form stars. Yes, but if it's too hot, gravity loses out and it simply can't rein in the molecules. So that's a bit of a mystery in this particular galaxy that needs to be resolved. Now, here is an interesting galaxy that is regarded by astronomers as the most similar galaxy to the Milky Way. It's NGC 3949 in Ursa Major. It's 50 million light years away, which is roughly the distance of the Virgo cluster, a little closer. And it's very similar to our galaxy in terms of the number of H2 star-forming regions that are in it, in terms of its having a bar, in terms of its size and its classification, an SBC galaxy. So this may be what we look like from afar, if we, of course, could never get such a picture, which we can't. Now, here's a record holder. Those of you who have seen some of my past programs have seen this slide before. This is the currently confirmed furthest object ever detected in the universe, thanks to the JWST. It is a galaxy in sextants called HD1. Its light has taken 13.44 billion years to reach us. The universe is only 13.8 billion years old, so we're looking back almost into the dark age before stars had a chance to form. Today, it lies at a distance of 33 billion light years, which means that we and it are separating at greater than twice the speed of light because of the expansion of the universe. Well, here is the closest galaxy cluster, the closest major galaxy cluster to us. It's the Virgo cluster, of course. It's 65 million light years to the center of it from us. It has about 1,300 galaxies in it and a radius of about 7.5 million light years. And it has a lot of famous objects in it. 3 Messier objects, M87, M84, M86, and the famous eyes. And this chain you see at the top of the image is called Markarian's chain. The black dots are just blocking out stars that would interfere with your appreciation of the galaxies themselves. Even from Earth at 65 million light years, this cluster is pretty big. This is how big a full moon would be in comparison to it in the sky, just to give you an idea. Really one of the richest fields of bright galaxies there is in the sky for us. Well, here is CLJ 1001 plus 0220 in sextants. This is a galaxy 11 billion light years away. It has 17 galaxies in it, and it's considered to be the most distant galaxy cluster detected to date. So it's a record holder of sorts. And here we have IC 342. Now, this is interesting. Maffei 1 was not discovered until 1967. And the reason for that is that it lies in the constellation of Cassiopeia, and we're looking at it through the disk of the Milky Way, which heavily obscures it and rendered it almost impossible to detect for quite a while. It's about 10 to 13 million light years away, so it's very close compared to most other galaxies. Its size is a little smaller than the Milky Way, about 75,000 light years across. And constitutes part of a group called the Maffei group, the 2 principal members being Maffei 1 and Maffei 2. And it would be one of the 10 brightest galaxies in the sky if we weren't looking at it through Cassiopeia. Now, I had an interesting experience. I gave a talk at the Milwaukee Astronomical Society back in October, and they had a unistellar EV scope 2 set up out back. And I had not seen one in operation before. And Matt Rhino, who is the factotum of that club, he does everything for them, had the thing set up and asked me what I wanted to see. Now, these were not great skies. The Milwaukee Observatory is triangulated by Waukesha, Milwaukee, and the Chicago Light Dome. So the skies are relatively poor, and we had some clouds in the sky as well. But it was clear toward Cassiopeia. So I said, well, let's try Maffei 1. And I was very dubious. And I said, well, I know it appears to be in a little trapezium of stars, which basically you can see here. And when he first turned on the instrument, it slewed to it, and it was kind of a gray screen with a couple of bright stars. And it fiddled around and re-slewed, and then it waited for about a minute. And then it went black. Boom, and there was Maffei 1 in the EV scope 2. So that impressed me greatly, what the power of electronic telescopes can be. Very remarkable system. Here we have a galaxy 5 billion light years away called RxJ 1347.5 in Virgo. And it has the X-ray luminosity of, you're going to love this number, 1 quatuor decillion ergs. It's the most massive known galaxy cluster we've ever detected in the sky. And turning to Draco, and again, if you've seen some of my past talks, you know this is one of my favorite objects to show people because it's so easy to find. This is a quasar, an active galactic nucleus that is causing a galaxy at great distance to be visible in amateur telescopes. Now, this particular quasar can be found by simply finding these 2 8th magnitude stars, which form a little triangle with a magnitude 12 star. Below that, a triangle, and off the triangle, a little arc of 3 14th magnitude stars. So a 10-inch, ideally a 12-inch. You have great skies, maybe less. You can detect these relatively easily. And this third one right here is the quasar. And what you're seeing when you see this in your telescope is light that has taken 9.6 billion years, that's twice the age of the Earth, to reach your eye. It's the furthest thing visible in a 10-inch telescope. It's about 2 trillion times further than Neptune, about 200 million times further than the nearest star to the sun, Proxima Centauri, of course. Larger amateur telescopes can access a 15th magnitude quasar, and it's called APM 08279 plus 5255 in lengths. When you observe it, and it can be observed in a 16-inch and certainly 18 and 20-inch Dobbs, you're seeing light that's taken just over 12 billion years to reach your eye in a universe that's 13.8 billion years old. It's the furthest object visible in amateur telescopes. And I promise you, if you ever see it, you will never meet anyone who has seen anything further live. I can promise you that because I've asked. Now here is an odd duck, J061352 in Auriga. This is 270 million light years away, and it's a galaxy with no stars at all. It was detected by simply noting hot gas in a vast system that constitutes galactic size. Very unusual object. And in Cetus, we have NGC 1052. This is a galaxy about 65 million light years away, which is an ultra diffuse galaxy. And what's odd about it is it has apparently no dark matter associated with it at all, which may explain its diffuse nature. And if you're ever feeling lonely, how would it feel if you lived here on MCG 01-02-015 in Pisces? 292 million light years away. It's out in the middle of the Pisces Perseus void. There is no other galaxy within 100 million light years of it. Were we to be in this galaxy, I promise you, whatever astronomical league they have there would have far fewer galaxy programs than we have. In fact, they wouldn't have even detected galaxies until the 1960s. NGC 45 in Cetus. This is 22 million light years away. And the reason the image is so crazy is because it is a very low surface brightness galaxy. It is more than 1 magnitude dimmer than the ambient night sky, which means dimmer than 22.0 magnitudes per arc second squared, or square arc second. Here's another image of it. You see how bloated and overexposed the stars are in order to image this object. It has a black hole in the center, about 145 million solar masses worth, and it's interesting because we know more about the exact location of the black hole in this galaxy than we do any other galaxy in the sky except our own galaxy, Sagittarius A star. So this is interesting for that reason. It has, however, no what's called galactic habitable zone. Now, this is a controversial concept. A galactic habitable zone, we're all familiar with habitable zones around stars. That is, you can't be too close, you can't be too far, temperature has to be just right, you can't be too close to a red dwarf because it's a flare star. We know about habitable zones around stars, but there are some people who believe there are habitable zones in galaxies too, and these would be zones where the metallicity of the stars is high enough that there's plenty of material to make planets, and areas where there is a low chance of having supernovas, gamma ray bursts, or other catastrophic events. But many astronomers doubt this galactic habitable zone theory simply because many stars and galaxies change orbits and carry their planets with them, closer and further from the center, depending on interactions with other galaxies. Well, this is an old favorite that most of you have probably observed, Messier 64 in Comet Berenices. This is the famous Black Eye galaxy, 17 million light years away. What's interesting about this 8th magnitude galaxy is that it suffered a collision about 1 billion years ago. And as a result of that, in the interior, the gas and stars are rotating in one particular direction. Now, the stars in the outer part are rotating in that same direction, but the gas out here is rotating in the opposite direction, which is very strange. And this is true out to a distance of about 40,000 light years. And that's thought to be a result of that collision. This is just an interesting looking galaxy in Pisces, NGC 474, about 100 million light years away, that is covered in tidal shells and tails. It appears to be caused either by its absorption of gas from neighboring NGC 470 over here, or because of a double collision, that is, two galaxies that collided and passed through each other twice, followed by a merger that would have left these shells. And which of those two is the case is not yet completely known. This is, of course, the famous tadpole in Draco, UGC 10214, 400 million light years away, and that tail of stars is 280,000 light years long. It was caused by a close interaction with a neighboring galaxy that you can see circled in yellow up here, that whipped around this galaxy and pulled out this streamer of stars. Many of those stars have achieved in the tail, escape velocity from the galaxy and will reform into probably dwarf galaxies themselves. Some will settle back into the main galaxy. Here we have a galaxy in Pegasus, NGC 7674, 380 million light years away. And the interesting thing about this that you can't really see is that it has two black holes in its core. They're only about a light year apart, too. A very unusual factor for this galaxy. And in Perseus, NGC 1277, the galaxy of interest here is the one in the middle, and it's called a relic galaxy. No stars are thought to have formed in this galaxy for the last 12 billion years. Most of the stars in the galaxy are now over 7 billion years old, and much older than that. And all stars in this galaxy apparently formed in a space of just about 100 million years at a rate about 1,000 times higher than star formation rates in the Milky Way. The black hole at its center is enormous, 17 billion solar masses, and it constitutes 17% of the mass of this galaxy, which is the largest black hole mass to galaxy ratio we've ever detected. A real beautiful galaxy is this one. It's often referred to as the dolphin guarding its egg. Just one little problem with that. Dolphins don't lay eggs, as you know, but nonetheless, that's what many people refer to when they describe NGC 2936 and 37. These galaxies lie 352 million light years away. They are reachable with 10 or 12-inch telescopes. One thing you will notice is this galaxy is being badly warped by this elliptical galaxy here. And what's happening is the gravitational interaction between the two is causing a lot of star formation on the near side of NGC 2936, and it's causing dust to be ejected out the back as a result of this rapid rotation around NGC 2937 down here. And here's another very popular galaxy. This is the fifth brightest galaxy in the sky, NGC 5128, often referred to as Centaurus A. It's 13 million light years away, and it's the furthest naked eye object that has been detected. I think Stephen James O'Meara detected it visually from a southern location at one point. It's a lenticular also, which has elliptical qualities, but also evidence of a spiral from which it's probably forming. It has a high, very substantial set of relativistic jets emanating from that black hole, and you can see them here with the lobes at the end. It has X-ray jets that are thousands of light years long and radio jets that are millions of light years long, and there's a lot of star formation going on in the disk part of this lenticular galaxy. NGC 660 in Pisces, it's only 45 million light years away, and it's a polar ring galaxy. The ring, however, is not really polar. Polar would be wrapped around like this, but this is inclined around the galaxy in a very odd way. And this apparently is a disk galaxy, a spiral that captured material that is now strung out as a ring. And the ring is full of red and blue supergiant stars and very recent stars, stars that formed in the last 7 million years. So that's why you see all these bright clashes of stars in the ring. That's where all the activity is taking place. And of course, we have the Cartwheel Galaxy, another ring galaxy. Lenticular ring, it's called. It has a diameter of 144,000 light years, so it's a little bigger than the Milky Way. In the outer ring, once again, you have a lot of star formation going on, hence all this bright activity that you see here. And was probably formed by a collision, if you imagine a bullet blasting through the center of the galaxy and causing a shock wave that drove material out into the ring. At least that's the estimate. And the spiral structure is starting to form again. From the core, you see the beginnings of spiral structure in this particular galaxy. But if you want a perfect ring, just go to Hoag's object, of course. This is in Serpens, 600 million light years away. No bullet has been found. If there's a galaxy that pierced through a spiral and caused the shock wave to make a ring, we haven't found the bullet. So some astronomers think that it may have been a barred galaxy and that some sort of bar instability may have caused the formation of the ring. And to give you an idea of how big this is in the sky, it's about the apparent diameter of Jupiter, about 45 seconds of arc. It has a diameter a little bit bigger than the Milky Way, but oddly enough, only about 8 billion stars, way less than the Milky Way's 2 to 400 billion. And if you've ever seen videos of those horrible fog-induced interstate collisions where 70 cars crash into each other, this is astronomy's version of that. This is a collision, not of galaxies, but of 4 galaxy clusters that are ramming into each other. It's 5 billion light years away. And what is happening is there's a 13 million light year long stream of galaxies, gas, and dark matter that are all flowing into a region that's already full of matter. And the result is this circus of activity going on here. These are galaxy clusters that actually collide with each other and continue to do so. So I'll leave on that note, and thank you for the opportunity to join all of you tonight, and I'll stop sharing.
Okay, goodness. Some really amazing and beautiful galaxies. I think I love that one with the arms were stretched out so far, so it's so cool. Let me do this. Okay, here we are. And I don't know, how do you guys feel seeing all those galaxies? What's your favorite?
They're all pretty amazing. Hoag's galaxy is really interesting. I'd love to be able to image that, but I think it
Yeah.
might be a little for me.
Yeah, the jellyfish one, the one that looked like it was like a spiral that was crashing into an elliptical,
I'm really intrigued with that jellyfish galaxy.
yeah, me too.
Something
Me too.
like to know what.
These are a lot of galaxies I've never seen before. So good job, Chuck. That's really cool.
Thank you.
So
The last
I'll
couple
chime in.
Matthew,
Last
Uh,
couple of
should
months,
be-
I've been imaging irregular galaxies that are kind of like the Magellanic Clouds, but a lot further away.
Right.
Yeah, Maffei 1 should be visible through a moderate-sized telescope. I've never seen it, but I should like to see it next opportunity. It's not that faint a galaxy.
And as for me, I loved some of the detail I saw in that image of Centaurus A. I've seen lots of images of it. That one looked like you could pick out a lot more detail there. That was interesting to me.
Yeah, pretty far south, but it can be seen from southern part of the United States. So, well, let's
Scott, I think
Scott, you muted yourself again.
You're still muted.
Yeah, you're
about that?
unmuted.
There we
Now
go.
Is that
I can hear
okay?
you.
Perfect.
Technology always gets you.
149 of these, huh, Scott?
149. That's
And he's
right. Only
muted himself in
149
about
more to
half
go.
of them.
That's right. That's right. So, but
Watch me mute myself now when it's
yeah,
my
I didn't
turn.
even
I'm
know I
gonna hit
muted
mute.
myself
I know it's
either.
coming.
That's
Karma.
right. Well, anyhow, I wanted to introduce Ron Breacher. Ron is an amazing astronomer, astrophotographer. He was at the Northeast Astronomy Forum with us, and he's just a very, very nice guy to talk to. When he's on Global Star Party, he really opens up to what he thinks and how he feels about his exploration of the universe. His images are stunning. And if you're lucky enough to get on his distribution list for his astrophotography, he'll pop one in every other day or so, and it's just so much fun to open it up and just see something, that your mind is about to be blown. Okay, so it's really cool. But you are going to talk about unusual galaxies, so
There's gonna be some unusual galaxies in my presentation.
I see, but your
But,
talk is
but
called
I've got
Living in
other
the
things.
Present and Viewing in the
I've got
Past.
other things to talk about.
Very good.
Actually,
Okay.
what I should be doing is sharing the whole screen here, and then I can present it as a slideshow.
Mike Overacker
Right.
in the group is saying that he has observed Maffei 1 with his 15-inch Dob. Very good.
Cool. I haven't seen Maffei 1.
Me either.
Anyway, my presentation, I always tie these presentations to the invitation that Scott sends out to all of the ambassadors for the global star parties. And so this talk is called Living in the Present, Viewing in the Past. And really, you'll see where I got my idea for the presentation when I talk about what Scott talked about, which is trails of time. And then I'm going to just provide some context on what it means to move at the speed of light, and that we're always looking into the past. And then we're going to look into the past of the universe by starting close to home and looking at things further and further away. And I get my mind blown every time I look at this stuff. So hopefully you'll share in the fun with me. So there's a lot of words here. You can read them on your own when you watch the video later. This comes from Scott's message to us about the theme of tonight. And here's what's important to me. The idea that light from distant stars reaches us only after traversing the cosmos for millennia. In other words, it takes time for those photons to reach us from wherever they started their journey. The idea that everything is connected, that everything is part of a grander interconnected cosmos. And continuity, which is the notion of persistence of time and natural processes across the cosmos. And again, you know, this kind of stuff can make you feel really small. I think that's kind of a glass half empty view of the world. Or it can make you feel like you're part of something really expansive and glorious. And that's the glass half full view of the universe. Definitely my glass is half full. So if you were moving at the speed of light, you couldn't just instantaneously get around the Earth to the moon or to the sun. It takes time to get to those places. So it turns out it would take you a little more than 1/10 of a second to go around the Earth at the speed of light. If you wanted to go to the moon, it would take you about 1¼ seconds. And just to get from the Earth to the sun would take around 8 minutes and 20 seconds. So light travels fast, but it doesn't travel infinitely fast. In other words, light has a speed limit as well. And so what that really means is that everything we see in the past, whether it's seeing a person across the table from you, or whether you're looking at galaxies, the light has to take time to get from that place to you. And, you know, I gave you some times in our solar system. The nearest star, light takes more than 4 years to get to us from there. Galaxies, we're talking about millions or even billions of years. So whenever we look at anything, we see things as they were, not as they are. And the further away something is, effectively, the further back in time we're seeing it. And there's a really cool 3-dimensional aspect to this that I'll point out when we get there. So let's start in really close. Of course, this is the moon. This is probably one of my very first astrophotos that I shared with anybody. It was on February 20th, 2008. It was about -25°C in my driveway. And I was using an astrophysics traveler and a digital Rebel camera. And like I say, -25°C, I took the picture on the left before the eclipse started. I took the picture on the right at mid-eclipse, and then all of my equipment froze. My mount wouldn't track, my camera wouldn't shoot. I was just really lucky to get this. But of course, this is looking back 1.25 light seconds. If you're looking at the moon, you're looking back in time by more than a second. Here's another eclipse. This time it's an eclipse of the sun, partial eclipse from 2014. And now, if you're looking at the sun, of course, with the proper eye protection, you're looking more than 8 minutes back in time. You're seeing the sun as it was more than 8 minutes ago. Solar system objects, I haven't tried to give a distance. The main image here shows bright Venus and to its upper left Jupiter. Then there's an image of Jupiter by Daryl Archer, a friend of mine. Of course, the distance to solar system objects depends on where we are and where it is in its orbit relative to us, but it's on the order of light days to light months, not light years. Comets are another type of object. They're part of our solar system, much further away. These are 3 of the comets that I've been lucky enough to image. None of them have David Levy's name attached to them, but maybe one of these days. But at any rate, these again, they vary in their distance, and therefore how far back in time we're looking varies, but it's again on the order of light months, maybe to light years when they're first detected coming back into the solar system. But now let's look outside our solar system, but inside our galaxy. And here we're looking at the Horsehead Nebula, very famous Horsehead Nebula. It's actually like a puff of smoke, a column of soot that is between us and the glowing IC404 behind it. That is an emission nebula being blotted out by the Horsehead soot. And this is about 1,375 light years away. Most of the objects are in that range of distances, and also in the bright star Alnitak is in that range of distance. So this is both emission, reflection, and dark nebulas inside our galaxies. Going a little bit further away, this is a supernova remnant, the Veil Nebula, and it's about 2,400 light years distant, 2,400. And this is a very large object. It's really beautiful in my 20-inch scope with a nebula filter, but of course I can only just get the left side and maybe the brightest part of the right side in a single eyepiece view because it's so large. It's about 6 or 8 times the size of the full moon on the sky. Going a little further, timing is everything. So the cluster here is Carolyn's Rose Cluster, NGC 7789, and it lies about 6,700 light years away. These open clusters tend to have a few dozen to a few hundred stars, maybe even a few thousand. They're very different from globular clusters, which I'll show you shortly. These open clusters are sometimes called galactic clusters, and they lie within the spiral arms of our galaxies. Now, you probably, while I was talking, noticed that red star blinking on and off. That star is not part of the cluster. It's in the foreground, just over 1,000 light years away. I know that sounds crazy to say that 1,000 light years away is the foreground, but there you have it. The universe is immense. That's a variable star WY Cassiopeia, and this is a composite of 2 images taken 3 years apart. Once when that variable star was at its maximum, and once when it was at its minimum. So the universe isn't static. Things are happening in there all the time. This is a brand new photo. I took it last night. In fact, I took this image. This is star cluster NGC 6791. Again, it's an open cluster. It's about twice as far as Carolyn's Rose at 13,300 light years. And it's in the constellation Lyra. It's very, very beautiful to look at in a 10-inch or so Dob or bigger. Really quite beautiful. It's about the size of the moon on the sky. And like I say, I took this image last night. So compare this open cluster to a globular cluster. This globular cluster now is 34,000 light years away. This is Messier 3. And rather than having a few hundred or 1,000 stars in it, it has a few 100,000 or millions of stars in it. The other thing that's different between globulars and open clusters is that whereas open clusters are within the spiral arms of our galaxy, the globulars form a halo around the main part of the galaxy. And most spiral galaxies have globular clusters, maybe all. Globular clusters come in a bunch of different flavors. They can be very, very dense, like M3, or they can be much more sparse, like NGC 5466. And NGC 5466, again, is almost doubling the distance compared to M3 at about 52,000 light years away. If these numbers are starting to sound really big, put your seatbelt on, because now we're going outside the Milky Way. And now we're going from thousands of light years to millions of light years and more. This is a very well-known photographic object, also easily visible in a telescope, modest telescope, visible to the naked eye in decent skies. And it's one of the closer galaxies at 2.3 million light years. And you can see a couple of satellite galaxies, M32 and M110, accompanying the Andromeda galaxy. Going a little farther, 10 times farther, in fact, Messier 101. So Messier 101 is also called the Pinwheel Galaxy. This is 21 million light years away. And if you look around the field, you can see it's dotted with other galaxies, some of which are part of the M101 group and some of which are far, far in the background. You can also clearly see in M101, particularly here at the lower right, oops, let me go back, at the lower right, some of these pink knots of hydrogen that are kind of like the Orion Nebula in our own galaxy. This is NGC 4567 and 4568 on the left, and NGC 4564 on the right. The galaxies on the left are interacting. They're a long way away from merging, but eventually they'll merge to form an elliptical galaxy. All three of the main galaxies here are more than 60 million light years away. So we're just getting further and further. And I'm not sure how easy it is for you to see, but up here, for example, there's a small galaxy, and over here another one, and over here another one. And all of those are much, much further in the distance. We'll talk about some of those in a moment. Galaxies don't appear in the sky by themselves too often. Often they appear in clusters of galaxies. And this is an example of a cluster called the Perseus A galaxy cluster. Obviously, it's in Perseus. And all of the fuzzy things that you see in this picture are galaxies. And the center of the galaxy lies about 250,000 light years away. For a long time, this was the furthest object that I had ever imaged. But all of these images are mine, and we've still got some distance to travel yet. So I'd like you to look at this. I actually had to put a red box around the name of this object because there's so much yellow in the image, it would have been hard to find. This is the Able 779 galaxy cluster. It's centered on the biggest galaxy, NGC 2832, and it's about 300 million light years away, which is crazy. But I want to draw your attention to all the labels that are in white, because all of the white labels are labels from the Milliquaz catalog. It's the Million Quasars project. So every white label marks the location in this image of a quasar. And these quasars tend to be at immense distances. I just want to show you a couple that are highlighted at the lower right of the image you just saw. So the quasar that's circled in the top yellow circle is more than 9 billion years of light travel time distant from us. And the lower one, 12.8 billion years. I don't know if you can see them as clearly as I can looking at my screen, but within the crosshairs, both of those objects are very, very clearly visible. And if you can't see them clearly here, go to my website, astrodoc.ca, and have a look at the image, which you can get at full resolution. You'll definitely spot them in the annotated image. So if you're interested in this, you want to see more of my work, check out astrodoc.ca. If you have questions and you want to reach me at rbreacher@rogers.com. The telescope and other equipment that I'm using now are shown in this picture on the right. Thank you to Celestron. They loaned me this fabulous C14 Edge, and other companies like Prima Luce, QHY, Optolong have given me some other great equipment to go along with it. And look out for my work in sky and telescope, amateur astronomy, and so on. I love to write. I love to teach. I love to do these presentations for the Global Star Party. So Scott, thanks for having me again and again.
Well, we love having you. So thank you very much, Ron. That's great. That's great. Okay. Moving on, as we make more trails of time here, we go back to, talking about Steve Edberg. Steve is, as I mentioned, one of my mentors. He's someone that really got me into amateur astronomy. It wasn't, not only through his lectures and stuff like that, but I'm standing in awe of this guy, he's still someone that is very awesome, but he is someone that I was introduced, and it was the first JPL scientist that I'd met. And from that moment, I just go, wow, this guy is working on something every day that's traversing our solar system, and he was getting people involved in what I think maybe one of the very first citizen science programs called the International Halley Watch. So I got the book, I jumped on that. I worked with a mutual friend that Steve and I had. His name is Mark Coco, and Mark could not stop speaking about how amazing Steve was, his energy, and his generosity to open up all of his knowledge and everything to a bunch of amateur astronomers who were trying to find their way around the sky. And Steve showed us how, and he showed us how to take some steps into science with the International Halley Watch. And now Steve tells me that after all this time, this is from 1985 and 86, that Halley's Comet is on its way back. So, Steve, I'll turn this over to you. Thank you so much.
Thank you, Scott. Whoops. Yep. Can you hear me?
Yes.
Okay. Thank you, Scott. I'm going to share my screen now and come up with, oops, I hope this. Got it. And go to the start. Right. Okay. And boom. Almost like I knew what I was doing. Thank you. Actually, I should show you. I dug deep down into a drawer to find this T-shirt,
We
which is
can't
the
see your
logo
T-shirt. Here,
of the International Halley Watch.
yeah, we can't see your T-shirt because
Oh, well,
you're sharing
okay.
your screen.
I can see
But
myself on the
at
screen.
the end, you'll have to show it. So,
Okay.
it's pretty
All right.
cool.
Anyway, so I had to do that since we brought it up.
Yeah.
It instead of now looking far, we're going to be looking close. And there are times when I wonder whether in talking about the flashes in the sky that are meteors, whether we should really be talking about astronomy or meteorology, or really something in between. But I'm not going to have that conversation today. I will try and bring in various threads, and I am punning significantly there with this conversation. So, with that as introduction, when I'm talking about flashes, I'm talking about meteors. When I'm talking about fuzzies, I'm talking about comets. And since Scott asked me to do this, put this together, I had to find out where Halley's Comet is. And today, just about an hour ago, Halley's Comet was and will be for quite a while yet in Canis Minor, a small dog in the evening sky. The magnitude, the prediction from the horizon system at JPL, which I still use and is open and available to anyone who wants to use it. You'll see the URL down at the bottom. It does predict a total magnitude for the comet and a nucleus magnitude. And a magnitude overall for the comet of 25.6, I actually don't believe, because this comet is probably doing nothing but just soaking up the rays and not getting warm enough to do anything out at its present distance, 35.3 astronomical units from Earth and 35.1 from the sun. And I think that it's more likely to be around magnitude 29.1. I did actually go and look for a picture of it, which I had seen, well, taken several years ago. And of course, it looked very stellar then, but I couldn't find that picture, and I couldn't find any other more recent ones. But the interesting thing that I did find, because I chased it down, was that actually the comet did turn around just pretty recently on December 9th, 2023, between 1 and 200 hours universal time on that date, and was at its greatest distance from the sun at that time. And it's swinging around. By the 28th of July, it'll be about magnitude 2 in 2061. So we've got quite a bit of time to wait for it to get around, but I'm hoping to see it a second time now.
Me too.
So we'll see what happens. Yeah, David, we'll go together. At least get somebody to push our wheelchairs out together. How's that?
I'll be out there with you.
Okay, Scott too. All three of
Me too.
us. Anyway, the unfortunate part of this for 2061, because we can look at these motions and make these predictions, is that overall the visibility is not going to be as good as it was in 1986 or 1910. But boy, if you wait till the 2100s, you're going to have a real whopper of a view of that comet. It's coming to about 10 million miles from Earth at that time. So that's where the comet is now. And why does that matter? Well, because this was what was captured in 1982, the earliest actually moment when the comet was captured on a return, 4 years before perihelion. I think at the time it was about magnitude 23. This was a digital image from the Hale telescope, the 200-inch 5-meter telescope there on Palomar Mountain. And this probably, well, I'm not sure if this was one of the 500 by 500 CCDs they may have been using at that time, or even 1,000 by 1,000, or if it was still a Vidicon or an Orthicon system. But either way, it was they did catch it, and that's what it looked like, which was not much. Of course, a lot changes in 4 years when it came to perihelion, really just about 4 years after this picture was taken. So what's the relation of comets and meteors? And the relation is this. Comets have two tails. Here you can see Halley's Comet in March of 1986. And one of those really good nights. This is taken by Bill Liller from Easter Island. And you can see its ion tail or gas tail, the bluish one here, and you can see a dust tail here. And while it all disperses over time and really rapidly, it doesn't mean it actually goes away. And so if by chance the particles that are in the tail of the comet they're actually orbiting with the comet moving away. So each particle has a slightly different orbit. It's severely affected by the pressure of sunlight over time. But the particles are still there. And if their orbits migrate in the right direction, we may eventually see meteors in the sky that radiate from a point that matches where they're all coming from, where the comet's orbit is as we view that direction. And here's an example of actually three meteors. Here is this happened to be a Geminid, two Geminids, one here right at the end of this trail. And if you draw these back, they meet back here somewhere near the constellation of Gemini, the twins. And then there's one meteor that we commonly call sporadic, or it's at least it has no apparent membership in among other meteors that might be falling at the same time over that night. So sporadic is typically the name, but it could be such an infrequent shower that we can't even identify it. And I just kind of got lucky with these, but it makes the point that there's a lot of dust out there from a lot of objects. Now, how many you might be wondering? And I will actually tell you, I was surprised when I got this table put together, because the last time I'd actually looked at this, we only knew about a third to maybe a half of these assignments of parent bodies to meteor showers. So the second column lists some of the major and a few minor meteor showers through the whole year. And interestingly enough, many of them have now been identified with specific comets. You can see the Eta Aquarids are assigned to P. Halley. That means the first periodic comet that was assigned, known as a periodic comet. Here is 7P Pons Vinici. And down here again is 1P Halley with the Orionids. So how do these assignments get made? And it's a matter of, first of all, a lot of work getting the meteor orbits determined, and that is possible with the equipment we have nowadays. And in fact, nowadays, 100 years ago even, this was being done. And it's also because we now know a lot of orbits for a lot of objects. If you look carefully, you'll see that a lot of these are not a lot. A few are not comets. The quadrantids are due to an asteroid that has no other name, but it's a known asteroid, so it has a number, 196256. A lot of comets coming down here. And in fact, in this set, 2004 TG10 is assigned to the northern Taurids, and 3200 Phaeton is the parent object, again, an asteroid that is the source of the two Geminids that I showed you earlier. It was also the source of the exchange of between two betting astronomers on whether or not Phaeton would end up showing that it had some cometary activity. It did not. And so I understand a case of Scotch went from one of those astronomers to another on the basis of no detection of any cometary activity. Well, now let me move to Halley's Comet and its orbit. And I'm going to mention again that horizon system. I got this, I asked for it to show me what the Halley's Comet's orbit was, and this is it. You can see it coming here. It actually has just passed aphelion, its most distant point in the sun, and it's going to start falling towards the sun in this direction. Now, the reason I'm doing that, and you're thinking, well, wait a minute, aren't we looking kind of down on the solar system? And I'm saying you're absolutely right. But Halley goes around the sun backwards compared to the motions of the planets. So while they're going around counterclockwise, Halley is going around clockwise. And that ends up presenting part of what we see with the meteoroids that we have seen with that, the Eta Aquarids and the Orionids, with a much higher speed than is common. Also notice we usually see orbits placed just on paper, and it looks like a long cigar on the same plane as the planets, and it goes out beyond Neptune, and certainly this goes out beyond Neptune. You can see that, but what you can't usually see is that it's the shift in the plane that it has, the inclination of its orbit. And up here I've magnified that, and I'm sorry it's not quite as easy to see the gray bars here, but they are up here. Halley's Comet in white, and it's going up well above the orbit of, or the plane of the solar system here. Not a huge amount, but certainly enough that we have to have the situation where all those separate particles that get dropped every time it goes by the sun eventually change their orbits enough for two things to happen. First of all, they have to drift in towards the sun or out from the sun, depending on which side we are, but they also have to find their way such that they are close enough to us that their orbit intersects Earth and that Earth collides with them. And that is what ends up giving us a meteor in the sky. And so this has two options. One happening, actually it's over here with the Eta Aquarids, and the other side, the Orionids in October. And so that is why we have meteor showers. So what are we missing? Now, there is this interesting link that we have to them, and this takes us really from life on Earth all the way out to the supernova that exploded and started the formation of the solar system back 4.57 billion years ago, and bringing the molecules necessary to what became our planet, and all the comets that must have impacted the planet over time to have delivered a lot of those molecules and some of the water at least to our planet. So when you see one of these meteors, think about what's happening. What you're seeing is the light generated as the dust particle, roughly the size of a grain of sand, is frictionally destroyed, heated up by the collision with Earth's upper atmosphere, about 100 kilometers, about 60 miles above the ground. And so we get to see that light. Sometimes when they're bigger, we get a much brighter meteor, a fireball out of that. But I've never seen an Aquarid or Orionid fireball. And in fact, the best best geminid fireball I saw was just last December, and it reached between -8 and -9.
Wow.
So the Eta Aquarids are visible starting about the 19th of April, detectable is the way I should say it, to about the 28th of May. We missed the peak by a couple of days, but you could still see some. The rate is currently quoted as about 40 per hour. I used to think of it as being 30 per hour, but I have to tell you that when you look at these lists, it's important to remember that what they're telling you is the zenithal hourly rates, the ZHR, which requires perfect conditions of weather and transparency, a very, very good dark sky, and your eyes being able to see a full hemisphere of the sky all at the same time. And really, most of us can't do that. And so what I will tell you is that under average conditions, with being comfortable in a decently dark sky, you might normally see about 20 per hour as you made observations of this at the peak. And for comparison, the sporadic meteor rate is typically about three per hour. The meteors will not become visible until Aquarius rises in the east sometime after midnight, an hour or so. And then the rest of the night, you have the chance of seeing them. This is got illustrated to me very distinctly when I was observing those 1998 Leonids, where the shower just was doing nothing. And as soon as the radiant rose, meteors started falling, including one that had about 120-degree path along the sky. It was skimming the atmosphere, just fantastic. Not bright, but covered a long stretch of sky, which of course shortened as the radiant got higher. I mentioned threads here because, in fact, when you think about a comet and what it does, each time it makes a pass around the sun, it loses dust, and that dust migrates, as I mentioned before. Also, because those dust particles all came and were released by the comet in one particular perihelion passage, when it was closest to the sun, they form a stream of their own that can be associated with the perihelion date. So in this case, the thread of meteoroids that we are crossing this period from April into May was released during the comet's perihelion passage in 984 before the Common Era, BCE. And so we're talking about seeing things that are, well, almost 3,000 years old, that got released almost 3,000 years ago. And then again, just for the record, coming up, we will have in October from the 2nd to the 7th detectable Orionid meteors, with the peak around the 21st of October at 6 hours UT. This rate is somewhat variable, also a little lower. And as I mentioned, I would still also recommend to you that, or just remind you that it's not going to be very busy even under average conditions. The map here shows where the radiant is, and over time, just because everything's moving in the solar system, the radiant moves. It doesn't move much usually in one night's time, but over the 2 or 3 weeks to 5 weeks that you can see something like this, you can detect the radiant moving, both for the Eta Aquarids, Orionids, and other meteor showers as well. And again, rises about midnight, and you should be able to see them, except that there's going to be a gibbous moon that will be pretty much interfering with a dark sky. So this is not an especially good year to watch for the Orionids. One other thing is that these meteors are quite fast because we are running into them more or less head on. And so they travel at about 66 kilometers per second. That's about 36 miles per second. And so these are very brief meteors moving quite fast on the sky. Something like the Geminids are much slower. And if you are fortunate enough to see a Draconid shower in early October, those are even slower yet because those meteoroids are actually catching up on Earth and managing to fall just a little bit faster than the minimum velocity, escape velocity that they would be falling at if they came from infinity without any motion. So I think that's it for me. And I will stop sharing and
Okay. All right. So that's great. David, I know that you and Steve have been very long time friends. And
40 years, David.
yeah, you're muted there, David. You are
David,
muted.
you're muted.
David, we can't hear you. You're muted.
You are muted.
Man, we
can't
wish
hear
we
you,
could hear.
David.
Oh, we're missing something that,
It was amazing.
yeah. David, you were muted that whole time. You got to hit your button.
You're still muted.
Maybe we can you unmute him, Scott?
No,
Okay.
Here, I can ask to unmute. Here we go. I think he realizes what's happening right now.
David, say something.
He is saying
Can't hear
something.
Okay,
you.
how's that? Is
Now we
that
can
there
hear
we
you.
go.
now? Okay, sorry about that, but I always enjoy your lectures, Steve, and especially this one, because just last night I was observing meteor showers, but not the Eta Aquarids. It was the May Libra meteor watch for me, and I saw one faint one from that little shower coming out of Libra and right into my telescope, and it kind of burnt a little hole in the mirror, and so I had to paint it with barbershop powder. Anyway, so that's kind of what happened. But my friendship with Steve actually began with the Halley watch. We had a wonderful, long friendship during that time, punctuated by one administrative meeting. Steve was in charge of the amateur observations net, and I was working with Steve Larson at the near nucleus studies net. And we were kind of paying attention, and then Steve started to tell jokes, whispering jokes, and I would start laughing, and everyone would kind of stare at us, and I kind of get very, very, very quiet. And then Steve would come up with another joke, and then we just started laughing and laughing until after a while, the meeting stopped, and the person running it looked at us and said, "Would you two guys please grow up?" And I'm happy to say, Steve, that I don't think we ever did. And
We haven't.
But anyway, it's been a long and pleasant friendship, and
Yes.
and it's really good to see you again and to see you still active in the field. And I hope I'll see you in person at some point. Thank you, Steve.
Likewise,
Thank you,
David.
Steve. Thank you. All right, that's great. Well, David, we've got Adrian Bradley is up next here. Adrian's work is getting, during the last Global Star Party, he announced that his work was about to be published in Astronomy Magazine. So it was a lot of fun. David Eicher was on with us and was also talking about Adrian's work in the magazine. And but some of the people that were in the audience were remarking how they remember Adrian when he first came on to, and his progression in his work, just continues to get better and better. And I know that Adrian got a big shot of inspiration and energy from your comments about seeing some of his early works. And so I think that
Absolutely.
that's one of the best things that happens in amateur astronomy. You get to meet people that are going to, uh, you know, it could be a small comment. It could be, a night under the stars, where somebody says something, or shows you something, and that can just lead you on to this lifelong journey. And so, my journey is very similar to something like that. So, Adrian, thanks for coming
Yeah.
on Global Star Party, and we're going to turn the stage over to you.
All right. Well, thank you, Scott, and thank you for those of you who made that comment. Um I have heard that they've seen the images and that getting better and better. And I can tell you, like I did last week, that a lot of that happens when I took my focus off of trying to make these photographically beautiful pictures. Many of you out there are very good at doing that. And I focused on one simple thing. If David liked the photo, then there must be something to it. I stuck with the astronomy as the theme, and I said, it's a nightscape. It's something like I have in my background here, where you've got a nearly fully eclipsed sun here and the color of what's going on with taking the picture, doing composites, not to make one side overly more impressive than the other, but to really balance them. And I'll go ahead and share screen. And what you're going to see with some of these latest images, I just took them Sunday night. First, here's the first page of the article. I wanted to share that. So pick up your copy of Astronomy Magazine, or if you get to Zenio and you have your copies, if I exit to library, you'll have all your copies. So I not only am a part of one, I like reading Astronomy Magazine. So, really enjoying. So now going through the images that I took last night, and we talk about, I think it's Trails of Time. Scott, you can correct the
Yes,
theme tonight.
yes, that's the theme.
So Trails of Time, and the time moves on, and I ended up with a bunch of star trails from the composites I tried to do, and they weren't going to be the greatest, but this was testing something new that I'm looking to perfect, and that's to get with all of you who do this already, the stacking of your sky images to marry with a foreground. Now, my goal is I'm going to stack images using wide angle focal lengths like 16 millimeter. And in doing so, I'm hoping that the noise that you may see will be reduced with the stacking. Now, what's interesting is what you can see with a 16 millimeter lens. You've got the starfish here, I think M38, M37, M36, I believe. It's the pinwheel cluster, and then M35 over here in Gemini. And you see them all when zooming in. 16 millimeter lens, you can essentially look back at your image if you get it sharp enough and pretend you're doing binocular astronomy. You can see that you need a lot of work in blending in trees. Trees are some of the toughest things to blend in because your automatic software doesn't always pick up every single branch and every single dip, nook, and cranny in a row of trees in a forest. But I love shooting in a forest because it's the night sky there when there's no development allowed. We got to 21.6 on the SQM-L meter. And if you know what that means, this was a Bortle 3 sky as we were passing astronomical darkness. Here we weren't quite there. There's still this glow, the remaining glow from sunset. And I started testing what I could do. You see some dust lanes of the Milky Way here that was receding to the northwest on through to the north, which I believe this is Polaris here, and getting to the northeast. So once again, not every image is perfect, but every image is something for me to learn from. And so I still keep these because there's great stepping stones. This was using 35 millimeter, and we go in and we look at Auriga and we look at some of our star clusters. We can see we picked up, we picked them up. We don't have all the stars here because we're shooting at 35 millimeter, but now we've got this haze over here. It's greenish. I'm thinking maybe it's a cloudy haze covering M35 and this lower part of Gemini. There's M35 right there. It's greenish. So, we wonder if anything else could be going on tonight. Well, so here we are. Those of you that do astrophotography will be familiar. It turned out a bit faceless here, depending on how big your screen is. But you're looking at one of my mentors, Brian Adam, whom maybe later, Scott, I'll try and see if I can get him on the show. He's trying to catch the the inner flux nebula. I don't think I got the I word right. So M52 or M81 and 82, there's a flux nebula that's there that a lot of imagers, if I recall, would thought it was just noise and would cancel it out or get rid of it, but it turns out it's there. We're just looking through that part of the Milky Way towards those galaxies, and that nebula's there. So he's trying to capture it. Here he is next to his camper. Well, it's a RV, and he's working on it. Meanwhile, you have Cassiopeia, and at one point I found the stars of Cassiopeia. Don't ask me to find it again because now I'm not sure. Well, here's a double cluster, so that's what I used. And then somewhere over here, I think I traced them out. Double clusters here, heart and the soul, and the top crown of an auroral outburst that happened while we were at this facility. And then all of the other stars. This was a 30-second exposure and meant to recreate what it looked like to stare out at the night sky. None of this was easily visible. Especially we were killing our dark adaptation all the time with imaging. No one had a telescope here, but we were looking up at the sky, and it got good as Cassiopeia and Cygnus began to rise. So here, still struggling a little bit with our trees, trying to seamlessly move them in, because when you do long exposures, 241 seconds, you get star trails going through, and the star trails, the starlight pokes through the trees. So that means just if I do a more closer up image, I'm going to have to figure out a way to take a shorter exposure that will not create a star trail, but be at the same exposure level as my longer one. So some more experiments will be coming. Barnard's E, as you may know from other images, I like to see if Barnard's E is fairly sharp and if there's some space here. Once you can see that, you have Altair, Deneb, and then those of you that love to image this region, when you can see some of the detail, the North American and the Pelican Nebula here, then the Satyr region. Somewhere around there, the Crescent Nebula should show up. I'm not seeing it right now. Sometimes you miss amateur astronomy, sometimes you miss certain features depending on how you do the image. For something as small as the crescent, it pays to take longer images. But here you've got the Cygnus Rift, which is not always the most popular part of the galactic plane, but getting detail there, it's a stepping stone to getting more detail later on. This cluster, I believe, is an IC cluster that is in Serpens, and this cluster is an NGC object. I believe it's 6688, and it sits in Ophiuchus. So right here, you've got a boundary, and I believe this dark nebula actually sits in Hercules. That dark nebula didn't seem to come out too well, but it's right here. That's the plankton. I call it the plankton dark nebula. It's got another real name, but it reminds me of plankton. Those of you who do Milky Way imaging, you'll see this dark nebula in your images, and to me it just looks like plankton. So there we go. And then finally, one of the things I'm going to write about, looking to continue doing some writing and just sharing my story of capturing space from Earth, capturing our universe, and especially the part of our universe surrounding what we can see of the galactic arm. I want to get into what light pollution does and how it affects certain areas, even out here in an undeveloped part of Michigan, northern lower Michigan. We are not allowed to develop anything because this is part of a national forest. However, there's development and there's towns some 50 miles away, and those towns still, even up to 100 miles away, those towns can still kick up enough glow to interrupt what we could see if this were to go all the way down to the ground here. You'd see some of the bottom part of the scorpion right here would be easily visible if it wasn't canceled out by this distant town. So the effect of light pollution, some imagers will just take this out. One of the things I like to do is leave everything in, because it corresponds to something that's really there. If I take a good image and it's not an artifact or some smudge in my camera lens, it's really there. All these streaks are really there, and it remains to be seen if those streaks truly are, if they're satellites, planes, or little meteors. Most of the time, you can kind of tell. I would say that this is a satellite, but some of these streaks, like this one, that might have been a meteor. Now this is Sagittarius here, so not sure which meteor shower, particular meteor shower it would belong to. And this was taken Sunday night. So if you are going to image, pick a time in which you can go to bed in the morning and recover. I had to work after doing this that night and after my drive. It wasn't too much fun. Real quick story before I turn it over, Scott.
Okay.
Yeah, here, Trails of Time. This would be a perfect image for that. Trying to clean these up was such a bother that I just didn't do it. I just left some of those in. So that shows how far the sky moved as I was taking the land image. While I was doing this, I had an old unit that it's a compressor, and in a pinch it could jumpstart a car. Well, the compressor came on. I touched the button for it to come on. I couldn't make it go off. Now I've got other compressors. I've got a smaller one, but that old compressor drove me nuts. Could not turn it off. Closed it up in the car while I took the image. It was still going. I decided I did not want to listen to that noise while I was heading home. So, right at this very spot you're looking at, everyone, behind you, and I'm off the side of the road. I decided since the galactic core rose and I could see it, I wanted to get an image. So I stopped, got out. Behind you at this very spot lies a big yellow compressor that just would not stop trying to inflate a tire. Now you may ask, why didn't you just use it, give your tire some more air and it would stop? Well, if that didn't work out and I lowered the pressure in my tire, now I'm in the middle of nowhere with a bad tire. So I didn't do it. Instead, I gave that thing over to the animals who can use it over there, or if anyone drives by and they pick it up, and I'm using a different one. So this one I call the compressor shot because it was going off while I was trying to gather this image. So with that, I'll stop sharing my screen.
Okay.
Thank you all for having me on. As always, the adventures of doing night sky photography are in and of themselves sometimes worth it. And most of the time there's an image that I'll say that I miss, or it's an image that I've already taken. Really quick, I won't reshare the screen, so we'll go on to the next one. But I did stop at a site that I had taken an image before and just sort of looked out over the Asable River. It's a beautiful part of land. I had already done an image of the Asable River and looking up at the Milky Way as it was rising, and I saw it again. It looked like there was some haze in the sky around it, but I was reminded of the last time I crossed the Asable River and looked up and decided to just stop, take an image, and hope no one would run me over as I was taking that image.
Yes.
That's the challenge that you have when you're just stopping in the side of the road and taking images. You can get beautiful images, but you can also get run over. So I would advise everybody, be careful out there if you're going to look for images or ways to capture the night sky with whatever is surrounding you. And you want to be safe, know your surroundings. Some of the darkest places out there they could be some of the spookiest because it's really dark. There's no other light to guide you other than the one that you should be wearing on your forehead or carrying with you. And you really have to know your equipment because you may have to fumble around with it in the dark. Because as soon as you shine a bright light, you've lost your vision and now you have no idea what's around you. So be careful out there.
Okay.
Enjoy the night sky when you can get it. And Scott, I will
All
turn it
right.
back over to you.
Okay, I appreciate that. Thanks, Adrian.
One thing I would like to add is that I was listening to Adrian's presentation just now, is the variety of what you've arranged, Scott, for these global star parties. We have Steve Edberg talking about comets,
Yes.
and we have Adrian going right from the majesty of comets to the wonder of the night sky juxtaposed with pictures, Ansel Adams type pictures of the foreground.
Yeah.
And I just wanted to point that out. There's one of the beauties. Unfortunately, I'm going to have to depart at this point, but I will see you next
Okay.
week.
All right.
David, always good to see you. And I will be at Alcon. I forgot to announce
Oh,
that.
great. I get to
I
see
am,
you at Alcon.
yep, I am driving straight to your presentation on Wednesday. And I'm
Right.
going to pull up and it'll be great to meet you. It'll be great to meet you all, Scott. And if you're there,
Yep. Me
finally get
too.
to see you in person.
Me
And
too.
I like a couple years ago, I will offer myself up if there's a short talk that anyone needs to give at Alcon. I'll be happy to share some things. But I think the planning's probably already done, but definitely looking
You
forward
never
to
know.
seeing you
You
all.
never know. You should, if you want to give a talk, you should submit something to one of the officers there. they're
I can
often here.
submit it.
Chuck Allen's still in the background there. So,
Yeah, yeah,
um,
Chuck or Carol Lyerg, or Terry Mann.
sure,
I know
sure.
I've talked to him, and then I would be remiss if I didn't go without saying hola to Robert,
See,
who has the
yep.
moon pictures over there, and of course Cesar, which is why I said hola, hola, Cesar. It's good to see you again. We're
Hi
usually on
Adrian,
the
how
back
are
end of these
you?
global star parties.
I happy to watch your pictures in astronomy magazine. It's something that you
Yes,
deserve. I was so happy to know that that you have a printed pictures
Yeah.
because I am from another time. Maybe maybe one of
oh, good.
this we appreciate when we watch something printed. I see your picture with the astronomy magazine with your picture, and I need a copy for me.
Yeah,
Wait, that
Get a
somebody
signed
sent
one from
me.
Adrian, so,
Absolutely,
yeah.
of
I got to
course.
figure
I
out how to
need
do that. I
that.
got to get a few
Sure,
of them and
yes,
ship them out. Yeah, they'll be. Maybe I'll bring some of those to Alcon in Kansas City. Bring some
maybe.
signed
Okay.
copies.
yes,
Sure.
yes.
That might be an idea. But the Cesar, you were there, and David suggested to Scott, hey, bring him on. He does nightscapes, and
Yep.
Yes.
it's been a wonderful ride ever since. And of course, I'm always here, just sort of representing where I come from. There's so many lights. No one's as interested in the night sky unless they're laying on their back. And it's when I share this with folks in the city of Detroit, and I've had nothing but huge support from them. They get excited and seeing me do this, and they've also been a big part of just continuing to go. Bowling community, you'd be surprised the communities that see what I'm doing. Very few of them anymore are asking, and those are your pictures. They're just saying we love to see it. So
Wow.
I have to
That's
mention
great.
the Warren Astronomical Society, University Lowbrow Astronomers, Royal Astronomical Society of Canada. I gotta try and make a meeting one of these days. And I think and of course, out Astronomical League. And anyone else I've met has been a big part of the journey, including that gentleman that I took a picture of sitting there in the corner. So
Yeah.
but it doesn't stop. I mean, this all started when I decided I wanted to share my passion for astronomy, not chase a I want to be the best astrophotographer in Michigan. That didn't work so well. And but when it
But
came time to
you are better
share
than
my
you
passion,
imagine.
well, and that
But
maybe
because
there's some
the
imposter
productions that
syndrome going on.
you
I admit
make
that.
are incredible.
Yep.
But what keeps me going, knowing that my grandfather was a photographer, and now I have a chance to sort of pass this on to my kids and to pass it on
That's
to
cool.
everyone and
Yep.
just say, hey, go, if you have a passion for something, you got to go and do it. You got to see what happens and get the right people on board to help guide you along the way.
All
So,
right.
Yes.
so with that, I think, is it Cesar's
Yeah, we
turn,
got
Scott?
we got people waiting for Cesar to talk about this star party that happened down in Argentina. So
Yeah.
I'm
Well,
going
Yeah.
to
I will drop into the background, just listen on, and Cesar, come on.
Yes, and really, uh, thought in you, Adrian, because we had a sky incredible, was full of star with a Milky Way, totally printed in the sky. This kind of Milky Way that you can touch and you can feel
I would have
in
loved
a
it.
level that we in the star party we uh, say the coincidence or say the same that we forget so clear sky, like a painted Milky
Yes.
Way, incredible. Because I saw the Milky Way in each star party, but we was lucky to have a sky. And I thought in you, I remember you say, okay, Adrian, next year, because we are thinking in return to the same place. It's only 200 kilometers from our regular place where we go, that is San Rafael. Well, I start sharing my screen with the presentation. Let me know if you are watching this.
Yep, we can see.
Now,
we see your. Yep, now we see presentation
the
mode.
first slide. You're watching the first slide.
Yeah.
Okay, because we know that it's not easy sharing screens. It's full of something like glitches or some kind of problems. But okay, well, we had the Star Party Valle Grande, the 2024 edition. Our partners are Instituto Copérnico, that the director is Dr. Jaime Garcia, my friend. And I made with Jaime Garcia around 20 star parties, or 20 years we was making star parties. Only 20 years we are making together star parties, sorry. And really, we enjoyed every year that we can do it. Really, it's a great experience where we receive friends that we feel like family, and it's the incredible people that came to each star party every year to share knowledge or to share image or carry telescope, make the sacrifice that is go to a place, spend money going with a telescope, on share with the people, with another people. Of course, that I know that is a pleasure for everyone. Well, our business, Araco, is the sponsor. Naturaleza Turismo is the company of our friend Cecilia Luraski. Cecilia is she's a specialist in all that is turismo, tourist, and she made all about the hotel, you know, all the logistics. We working in this trio from many years. We are happy to share tonight the experience of our last star party. Our last star party was not in the San Rafael, in the Valle Grande, that we call it Valle Grande, that is near to San Rafael, the Rio Atuel. If not, we change for only logistics things of organizations. 200 kilometers more. 200 kilometers is around 150 miles, a little less. And we go more to the south and to the west, to the Cordillera de los Andes area. And it's 13 hours driving from Buenos Aires, and you have the options to go to Mendoza in plane, in flying avion. You can fly to Mendoza or San Rafael. We, for example, this year, we choose the organization, we choose go from Aeroparque de Buenos Aires to San Rafael, and rent a truck, go to the Los Molles, that is the area where we make the star party. Something that I show in the last global star party before go to the star party was this part of the map where you have some kind of lights, but this is a sky resort, and now these lights are turned off. And the quality of the entire area
Wow.
is excellent.
It's gonna be-
And this is doesn't exist this in this time of the year, because only they turn on the lights for ski, for skiing only in winter. And here we are in this area, and this area of Las Leñas is through some mountains that I'll show you the area how is. And the place is really interesting because you have a lot of mountains. Well, pictures can show more than my words. This is the hotel where we went. We make the star party, and mostly of the people and the center of dinner, lunch, or everything was in this hotel. But we used another hotel more near to this hotel because we was filled in the rooms. We complete the rooms and we was lucky to use another hotel more. This is the view from the hotel. What do you think? And this
Beautiful.
small location is Los Molles. It's very, very small, very, very small town. Really a beautiful place. Well, we started to put telescope in the field, in the area of parking. The place was excellent to use the parking area for telescopes. Of course, the hotel in the night turned off all lights. The quality of the sky was amazing. I like to show you the people, like, and if I remember the names, sometimes I don't remember the names, but the people from Argentina can put in the comments their names if I forget something. Okay. And Lucas Bañasco, Maison Agustín, Jorge Vila. I think that this here is the son of Lucas. Here you can see how this Explorer Scientific 127, Scott, is over Exos. This is the Lucas Bañasco equipment. And the first day, all people that came to the star party started to connect things and improve the things for the first night. We had 90 people. That is a good number for Argentina. Sometimes it's our idea is to return to more people to have more than 300. But at 90 people actually is a miracle. Here is the typical thing that I love from the star parties, the people that carry their stuff, start to put the tripods, and it's the folklore, is the things about the star parties that is the same in every place in the world, and I love it. More stuff, more gears, more telescopes, and a mix of a mix between Cassegrain telescope, Maksutov, refractors, Newtonians. It's something that is everywhere is the same. Here,
look at this.
yeah, yes. Here, Juan Pablo Patallo, Sergio Escauso, Alejandro Varelli here, but I'll show you more. Here, the flags of our company, the sponsor.
You got a nice place to get out of the
yes. Martin
Cold, if
Ruiz
you
is
want.
yes, the Exos too. Martin is a collaborator in the foro of PMCA
Okay,
with another guys
great.
writing some code for connect to ACR Plus, or they have more fun connecting than using the telescope. That is something that is a new style. Yes, and I appreciate this because the people can collaborate making a better thing over the stuff, over the years, and this is something that never appears, and this is great because it's something new. Here, I took the picture of Juan Pablo Patayo. In the end of the presentation, I show you the quality of the pictures that Juan Pablo took with this gear that is a Apple 80 Explorer Scientific over a EXOS 100. This is a funny picture because Juan Pablo was finding something in the track. When you need something that is in the impossible to to get, well, it was a funny sequence of pictures where Juan Pablo needed to go to get something from the end of the box of the track. And this is a fun picture too of Martin Ruiz showing like this is my telescope, my gear, and a picture of him in the preparing the night. He's a great astrophotographer too. Alejandro Varelli preparing a tripod. Alejandro Varelli is a great collaborator for about optics, optical forms and calculations over eyepieces, or he's a fan of Explorer Scientific eyepieces. He have a collection of 80 eyepieces in their own boxes. Roberto Claverier here.
Jeez.
Sorry, I took something. Wow.
It's a lot of glass.
Yes, I took too much sensitive the mouse. Okay, here, okay. Roberto Claverier here is a great collaborator for third parties. Here you have another staff mixing a Sibony telescope with a EXOS 100. The EXOS 100 are going to be popular in Argentina, really. And EXOS 2, in another configuration over another 127. A better picture of this. Sergio Escauso is a great astrophotographer, excellent he is a volunteer educating, he's an engineer, and he loves to educate kids about astronomy. He used an Explorer Scientific in carbon fiber. He's an Explorer Scientific fan too. Here is the gear of
nice.
Juan Pablo that he used, CWO camera, Sibony camera for guiding, EXOS 100 for as mount, and Explorer Scientific 80 millimeters APO
that's
telescope.
fun. That's great.
Yes.
Thank you.
Yes, wait to see the pictures that he made. Really
Juan
incredible.
Patalo is remarking, he says, you are the best seller of Explore Scientific telescopes.
I know to Juan Pablo from his 14 years old, the first time that he came to the store, with his father. He actually is like a friend. Is like he told me that I was a mentor for him. He told me this, but
Mm-hmm.
and I appreciate this.
That's great.
This is when where you selling this and you finish going to be a friend of your past customer. And really I was in Juan Pablo Patayo marriage
Sebastian
party.
Otero says 14, but he's 50 now.
Juan Pablo have
You have good friends here.
Yes. And yes, well, Juan Pablo, Sergio Escauso, and we went to Las Leñas. You can visit because it's very near. This is only at, I don't know, it's more than 15 kilometers. This is the Sky Resort. And we went in the morning to go to walking by the sky lines, you know.
Look how
The ski
clear
line,
it
so
is.
not the
I
ski,
mean,
the sky.
just,
Yes, it's a
so
beautiful
transparent, you know. It's very nice.
yes, absolutely. It's a very nice ski center.
Yes.
It's not the Cordillera, if not, we call it the Precordillera. Yes, we had in the morning every day. We have different trekking, visit another places. Really was an excellent experience for a lot of people. This is a picture of Pablo Barrios that took the picture of the people that go to the volcán Malacara. And this is a place where you can go and visit in our star parties. You have a lot of things. You have two different observatorios and a lot of things in the area to visit in the morning. And really, we had a lot of different experience. You can go to the ski center or here, the name of this is Valle Hermoso. It's incredible place. It's in another part where in this area outside, downside in this area of the mountain, in another place is the ski resort, the ski center. And in this area, you have a big, huge valley, and here you have the real Cordillera. And another side is Chile. Look that, it's incredible. You can go, it's all near to the place of the star party. Well, we love to eat. Argentinians especially, we love a good food. Is like music for our souls. It's beautiful, and we had an excellent meetings in dinners and lunch, talking with old friends, and this was a great part. Was a beautiful part of the night. In one of these dinners, we have music. Really was something of folklore. Very nice things. Here, Lucas Rocco, Agustin, my son, was like a percussionist.
That's cool.
Yes, because he studied something of music.
Yeah, he's an excellent astrophotographer too.
Yes, he love astrophotography. Yes, absolutely. Yes, and the best of things is that all people know together and talk. He, for example, Agustin, many times helped people about connections, about the connection that every day is more complicated, but it's more fun for the people that love connect different softwares or use Nina and connect the kind of mount in another systems. I would still love to give support for this. It's very interesting. Well, here it's part of the conventions, the talks that every night we offer every night. No, sorry, from the lunch time, from the after the nap to near to the we made a coffee break to talk more, not so extensive, but we think that first the people in the morning go to make trekking, visit another places in the area. After the nap to the evening, we have the traditional talks normally from professional astronomers or specialists. For example, the Dr. Anaí Granada, and she's from San Carlos de Bariloche. She talked about the B stars, for example. BA, I don't know to say exactly in English, but it's the kind of stars, for example, Octavio Aguilera. Octavio, it's, is a CONICET investigator. I know. I remember that he had the prize of a Explore Scientific Telescope because we make we typically make a sorteo with numbers. He was he had the prize of the Explore Scientific Telescope. I remember this, and with their friends they started to use. He's a doctor, astronomer doctor, and he started to use the Explore Scientific Telescope, the refractor of 90 millimeters in the star party. And they was happy, really, because sometimes, he told me that sometimes as professional astronomers don't have enough time to enjoy the visual telescope. Really, he was really happy with this.
That's great.
And he talked about question about planets. Marcelo Miller, Dr. Marcelo Miller, is a student investigator of CONICET. Marcelo told us about planetary nebulas. It was really, really interesting. Gabriel Bengochea. Gabriel, it's a friend. Today is the Gabriel birthday.
Oh, happy birthday.
Happy birthday, Gabriel. Yes.
Happy birthday.
Yes, it's a great friend. It's the guy that when you called me one time, I was returning with Gabriel from Asociación Argentina de Astronomía meeting. You listen to Gabriel. Gabriel say, "Okay, we are going to Buenos Aires, and we don't like to drive at night." Gabriel told me drive now because in the night the road is really dangerous. But I remember that we was together talking about this. I talked with you in a gas station in the road. I remember. Gabriel talked about after the bank. His specialist is a doctor in cosmology. He's really a great professional.
Very good.
Talking about inflation. Doctora Catalina Urrejola. Catalina told about riquezas, rich of the cosmos, or maybe treasures of the cosmos, exploration, exploitation. Okay, about meaning, asteroid meanings was really, really interesting. Federico Garcia. Federico is a genius that he is a specialist in X-rays, astronomy, and he told about the binary stars in X-rays. Alejandro Varelli made a talk about optics, the transformada, something like a Fourier transforms, or transformada de Fourier is in Spanish, is the, the formula, Scott, that, for the calculate the resolution in optics.
I see. Yes. It's important.
And yes, and they told in optics with Jaime Garcia. I don't have pictures of me and Sebastián Otero. Sebastián Otero give us a special variable stars. Sebastián Otero work in the American Association Variable Star Observers. I invite to the Global Star Party to Sebastián Otero because he have more things more interesting than me to talk, and I contact him to invite to Global Star Party. And it was really, really interesting, the talk that Sebastián give us. Adrian Nowick about spectrometry was an excellent talk. Here is Sebastián Otero, but I don't have pictures of me or the talk of me or the talk of Sebastián. I don't know why. I forget. sorry, Sebastián. Maybe talk in the YouTube comments and say, where are my pictures, Cesar?
So Sebastian says you will not be forgiven.
Yes.
This is a tough audience you have here.
Yeah,
Very tough. Yeah.
Yes, it's they are terrible because
he says
the entire year, Scott,
yeah.
they follow talking in the WhatsApp group and they are around 70 people at all time.
All talking in one group.
Okay. Yes. No, yes. The entire year they start talking to the next star party. The entire year. Yes. Rafael Girola, that is a friend too. That we know with Rafael a lot of years. And this is the something that the people give us, that is the capture of the screen capture of the cell phones, because Adrian Nowick, the same specialist in in spectrometry, he's an electronic engineer, and he support me to have an intranet with a transmission of all things that we have in the telescope, like a global star party, but it's presential, and you can get the image in the moment in your cell phone, and you can how do you say, save the image that over, like we can talk, or specialists over the kind of objects that we show in the moment. And Agustin made magic, because he had a go to mount with a telescope of near to 2 meters focal distance, and with a very small sensor, and Agustin put all the old objects in the center, there in the center, was a great for me. I felt really proud of myself because I said, no. You know that sometimes, look, this is the single image that Agustin, the astronomers say to Agustin, show that this picture and talk over the live image. For example, Centaurus A, Galaxia El Sombrero de Messier 101, and Messier 83. This is only a part of the galaxies and objects that we show in the moment in the star party, and was really, really fun because still talking in the night was a great experience. It's something that we are going to continuing for the next star parties, because you don't feel how do you say the quantity of the light of your cell phone to watch something. You can put the lowest bright in your screen, and really something that the people told us that it's okay. It's okay because we don't lose the perception to the low light or to the darkness. And it's it was a great idea. Put this in this star party. Well, this is the go to the night. This is the first pictures that I took the first night with the cell phone, but look the pictures.
It's really
good. With the cell phone. Yes. The Coke, the goes up, but look this. This is with cell phone too. It's a picture that took Santiago Mayese.
Look at that.
Walter Garcia put more time in the yes. Look that.
Wow. Cell phone again?
It's a sky for Adrian. It's a sky for Adrian. I thought that I remember they say, oh, okay, I need to call to Adrian and say, come on, Adrian. Came to eat asado. Yes. And you too, of course, Scott. Next year.
Me too.
Yes. March, in the end of March, prepare yourself because and Adrian and everyone that came to and make the global star party from live from Los Moches. Look, that is incredible place with the stream. It's full of things to visit. This is the area of the hotel. It's only crossing the road, where the road is anybody came in the night to this road, because it's the way to go to the ski center. The ski center that in this time of the year is empty, without lights. Anybody can ski can make a ski and ski in the grass.
Only. So how far by driving is it from your city?
From Buenos Aires, 13 hours. 13 hours.
13 hours.
13 hours. I think that is too much to make in a one night. I think that is one day. Sorry. San Rafael is a little less, and you can go in one day because are about it's 12, but 13. It's not real 13 because you have maybe you need to think in 14. But if you can go, you choose a small telescope and take a plane, because maybe the plane is cheaper than the gas for your car. Maybe you need to yes. If not, you can rent a truck or use your car. And I think that the best is go to the how do you say, to San Rafael, sleep in Rafael, and the 2 or 3 hours for the next day is nothing. Going to San Rafael City to Los Moches.
Right.
Well, here Nani is a woman that he worked in the Patagonia. His company is Patagonia Ski, and she give us a lot of pictures for the people. She loved to take pictures. Okay, quiet with the and it's lovely because you have your picture or with the people and the Milky Way, and it's magic. Look that.
Very nice.
It's nice, really it's nice, because the here is mostly the east, and you can see how the Milky Way is going up in the sky. Here is the area of Sagittario and Scorpio. Look that.
Beautiful. It looks like
Yeah.
the Milky Way is just pouring out of that telescope.
Yes, and this is yes, and this is the core
Or
of
filling
Milky
up
Way.
the
This is
telescope. That's what it's doing.
Yes. Do you know this telescope? This is Explore Scientific
Oh,
model
yeah.
too.
Yes.
Another one. Yeah. It's lovely telescope because it's a Newtonian, very nice to show. This is me and Miguel Magakian. Look that. You need to make a star trail.
Oh my God.
This is a picture
I
of
get
Nani
dizzy
too.
just looking at it. That's awesome.
It's a crazy two-star trail that made by women, Nani and Silvia Papaleo. They women are excellent for astronomy in all that you can imagine. That because I think that this is the hobby, the activity that we can share. Really I love the people that men and women don't care about this, but it's full of opportunities to mix with photography, with observation, with of course science. Well, come on, it's a great activity.
Yes.
Look that, it's incredible. The colors of different stars. I don't know where it is, but I think that this is the Southern Cross, but I don't know. She used, and here you have the path of something. Look that.
That's beautiful.
You can see the and something like a path of some star.
It's great.
Yeah, look that. Look this, the Magellanic cloud.
Oh, yeah.
Incredible. With a
Incredible.
This is a picture of Pablo Barrios with a small dog. Look that. It's a place where we need that Adrian Bradley came.
Mm-hmm.
It's the Disney for Adrian. Disney World for a picture of Martín Telechea. Well, this is the picture of Juan Pablo Patayo. We have another one that is beautiful in another position of Sergio Escauso. Both used the Explore Scientific 80mm telescope. Look at the Eta Carina Nebula, but look the field of view of this telescope is amazing. It's amazing. I'll show you the original pictures, and I put zoom when I finish this presentation. This is in Hubble palette Hubble palette filter, sorry. We was together in the picture of the growth. And wonderful. This is all that organizers and exposure that I say, I need to say thank you, because the quality of the people, it's amazing, really. I'll show you as fast as possible. I don't know if, let me. where I need to. Okay. And now, okay. You can see now the picture.
Beautiful.
This is this you can see the
Wow.
picture of it. Okay, look
Yeah.
that, because this is something that good optics can make.
Mm. And good skill. And good skill. Yes. That's beautiful. And dark skies.
Look the details.
Mm.
Look that.
Yeah. Yeah. So many areas where baby stars are being born, you know?
Yes.
Mm-hmm.
And it's full of details. This area is totally amazing.
Yeah.
He used Juan Pablo told me, I watched it in the night, and he used around 2 hours, 2.5 hours for
Wow.
this picture. Yes.
Uh,
Yes, the quality of the sky and the quality of the optics. In the quality and CCD, of course.
so much rich
And the
detail.
mount that
Incredible.
work really properly, Scott.
Mm.
You can feel, how do you say? You can feel, a ver, I don't know if okay.
I feel a sense of awe, you know, is what I feel. It's really amazing.
Look that.
Oh, yeah.
It's a craziness.
Yeah.
Look the
Well,
area.
you guys watching this, you got to consider getting down to the southern hemisphere. And probably
Yes.
your best shot for this kind of thing would be to hook up with Cesar and his group, because they'll take you out to, they know where to go, and they'll keep you safe, and they'll keep you fed, and you know, it'll be fun. It'll be fun.
Okay, I'm happy to share with you this, of course, with the people of that participated in the Star Party, and really, well, it's something like we made with all heart, with a lot of love.
Yep.
It's great that the people really enjoy this. Well, it's something like we enjoy, and we are happy that the people in the Star Party enjoy too.
Yeah, this is very cool. Very cool. Okay. All right. Thank you so much, Cesar.
Thank you
You
very much
a
by
great night.
inviting
And
me.
thanks to your audience. It was fun to have them watch and comment on your program, your presentation. So,
Okay, thank you. Thank you very much. Okay, hi, Robert. Sorry that maybe I was too extensive in the.
Good pictures.
great
Thank you.
pictures.
Thank you very
Yep.
much. Yes, it's the picture of Juan Pablo Patayo is really amazing. Juan Pablo really made a great work. Showed that the quality of explored scientific optics really are really
Now
good.
I want to buy one.
Yes. No, he have one. Yes. Yes, maybe he needed something bigger, but
Maybe.
yes.
You always need bigger. Thanks, Cesar. You take care.
It's a pleasure. Okay.
Good
Thank you
night.
very much.
Good night.
Good night.
Okay, Robert, thank you for hanging in there with us. We are running just a little bit behind here, I guess about 30 minutes behind, but a lot of great territory was covered today, so that's great.
Absolutely.
Thanks. So I will leave this to you, and I'm looking forward to seeing your presentation as I always do. So,
Alrighty. Well, let's do the great experiment, do the screen share, and see what kind of disaster happens. And come on, there we go. Whoops.
You have thumbnails.
And now do we have my title slide?
No, you have thumbnails.
Uh-oh, there we go again. Now how do I get out of this?
Here, I'll unshare you,
Okay.
and you can do it again.
Maybe whoops. Nope, that's not going to work. I just started the wrong program. I'm trying to connect to my observatory. Let's shut that one down and open up this one and get the slide up first, then go back to Zoom and see if I can share.
Yes.
Kaboom, working, great, already. Well, as usual, I title my stuff Postcards from the Moon, and because I like to share little tidbits about the moon and kind of get people reacquainted with the moon after all this time. Back when I was a kid, the moon was such a big deal, and then kind of faded away from amateur astronomy, and it's kind of my duty nowadays to bring the moon back into our fold, because it's something that's in our night sky most of the month. We can see it from the backyard. The moon doesn't care about light pollution, and there's so much to see on the moon, even with a very modest telescope. You don't need an enormous amount of power to really enjoy some of the things on the moon. So the whole theme of tonight's presentation, Trails of Time, we're going to press on here and examine some things that have happened on the moon over periods of literally billions of years. We tend to think of time on the Earth in shorter time scales because things on the Earth change more rapidly. We have weather, we have plate tectonics, we have oceans, we have the atmosphere that changes our Earth on a very short time scale. Millions of years, but on the moon it is billions with a B that changes happen. So again, the standard slide to remind you of the two primary landscape forming processes on the moon. If you see anything on the moon, it was either created by an impact or by subsequent volcanism. So that has left us a world that has the dark maria, volcanic, the dark regions that form the face of the man on the moon, and then the bright highland areas, which are the original crust of the moon that were not flooded by volcanism. So I will have shown these slides for the past two star parties, and I'll do it one more time before I retire them, because I want to remind everybody, once again, that the moon is a world that shows us a world that is rugged, yet it is serene. Shows us a world that is harsh, yet beautiful. It shows us a world that is alien, yet appealing. And a tortured world, but now calm. And finally, it's a strange world, yet it can become your friend if you take the time to look at it and understand it and know what you're looking at and become friends with the moon. So, trails of time. Of course, I mentioned things on the moon are measured in billions of years. You know, like Earth has undergone various epochs of geologic time. Well, so has the moon. Everything before about 3.9 billion years ago is considered to be the pre-Nectarian epoch. And then there was a brief period of about 100 million years, the Nectarian epoch, where many of the large features on the moon were created by the late heavy bombardment. And then about a billion-year period of the Imbrian epoch, where much of the volcanism occurred on the moon that created the dark maria. And then the Eratosthenian epoch that went on for about 2 billion years, and much of the subsequent impact cratering took place. And then the modern era, just the past 1 billion years, the Copernican epoch, where the moon has been fairly static save for the craters that we now see that have a ray system around them. Rays fade after about 1 billion years. So if you see a crater on the moon that has a ray system around it, it is less than 1 billion years old. So let's look at some of these features that go way back in time on the moon. A very popular target are the triple crater combination of Theophilus at the upper right, Catharina, Cyrillus next to it, and then Catharina kind of at the lower left center. These three craters arc around Mare Nectaris, and they appear about the 5-6 day old moon, and they make such a striking feature. You can see these in binoculars, but progressing through lunar time, we can clearly see that even though these craters, all of them are at least 3 billion years or older, they look radically different. The one on the bottom left, Catharina, a Nectarian epoch feature, at least 3.8 to 3.9 billion years old. And the same with Catharina, sandwiched in the middle of, Cyrillus, sandwiched in the middle of them. Not quite as degraded, but along came Theophilus, the upper right one, later on in the Eratosthenian epoch. So it's the youngest one. But as each one of these formed, Catharina first, and then Cyrillus, the shower of debris thrown out of the seismic shaking from the impact that created Cyrillus degraded Catharina. And then the same thing happened when Theophilus impacted about 3 billion years ago and did the same thing to Cyrillus. The impact shock degraded the crater, although the form of it collapsed and it was buried in the shower of ejecta thrown out from the last crater formed. Now this pattern is repeated again and again on the moon, where newer craters overlay older craters and degrade the older craters. So not quite perfect overlaps here, but these four craters that extend north from the Mare Crisium on the extreme right-hand side of the eastern side of the moon. I call these the stepping stones. You see Mare Crisium poking up into the field of view at the bottom, and then just above it, the crater Cleomedes, which dates from the Nectarian epoch, almost 4 billion years ago. And then above it, the smaller crater Burckhardt, which dates from the Imbrian epoch, maybe 3 billion years ago. Above it, Geminus, even younger, from the Eratosthenian epoch. It could be anywhere from 1 to 3 billion years old. And then up at the very top, the very degraded pre-Nectarian crater Massala, the oldest of the bunch, over 4 billion years old. And if you hear the name Massala, and the first thing you think of is the 1959 Charlton Heston movie Ben-Hur, you are dating yourself, because a very, very popular movie back then. And of course, Massala was Judah Ben-Hur's antagonist throughout the entire movie. A very classic movie. If you ever get a chance to see it on Netflix or something, I highly recommend it. Yeah, but moving on in the modern era, down on the south side of Mare Nectaris, we see Fracastorius crater, another Nectarian epoch feature between 3.8 and 3.9 billion years old. Now here we see it as a horseshoe bay on the south of Mare Nectaris. Now, mind you, when the impact formed Fracastorius, Mare Nectaris didn't exist. The lava flooding had not yet happened during the Imbrian epoch to create this Maria. So we've got basically this crater overlaying the rim, southern rim of the Nectaris basin. But when the lava flows started and took about 1 billion years to fill in these low-lying areas, it slowly filled in Mare Nectaris, paved it over, turned it into the round Maria that it is, but the depressed northern rim of Fracastorius, having formed on the tilted rim of the Nectaris basin, it allowed these basalts, these lavas, to flood into Fracastorius and create a horseshoe bay. So this whole process took over 1 billion years. First, the Nectaris basin formed shortly, very shortly after Fracastorius crater was formed, and then it took 1 billion years or more for the lava flooding to obliterate the floor of Nectaris and turn Fracastorius into a horseshoe bay. Showed this one last week when I was talking about floor fractured craters. But again, a process spread out over a long period of lunar time. The circular feature in the middle with the bullseye crater berg right in the middle of it, Lacus Mortis, the Lake of Death. Now, back in the pre-Nectarian epoch, the 150-kilometer crater that formed the circular ring you see surrounding Lacus Mortis, it formed during the pre-Nectarian epoch, and then for the next billion years, lava flows slowly flooded the entire region. Mare Frigoris up at the top, Serenitatis down south, and more or less paved over everything. And things were fairly flat for a while, and then along comes this Eratosthenian epoch crater berg, anywhere from 1 to 3 billion years old, and slams into the middle of it. So remember I said things on the moon or features are created by two processes, either impacts or volcanism. Well, here we have a process where an impact created the original crater that then filled in with basalt to form Lacus Mortis, and then finally it in its own right was again modified by another impact, the creation of berg in the middle of it. So all these processes spread out over literally billions of years, and that's billions with a B. So it's really hard to wrap your head around such extreme time spans, but this is the normal for talking about time spans on the moon. And the moon preserves this impact record because it has no weather, it has no oceans, has no plate tectonics to eradicate these features like what happens on the Earth. And moving along, Plato crater. Plato formed during the Imbrian epoch, formed on the northern rim of the Imbrian basin, which basically cradles Mare Imbrium, the man in the moon's left eye. But everybody who observes the moon quickly falls in love with Plato because it looks so different. A flat black floor instead of the traditional excavated indentation of a crater. But look closely at Plato, and you can see originally it was about a little over 90 kilometers in diameter, slightly larger than Tycho is today. And at the time, it had a central peak, collapsed terrace walls, rather spectacular ray system spread across the northern half of the moon. And then the Imbrian epoch volcanic flows happened, and internal flooding from below the crater through fractures in the crust underneath Plato allowed magma to seep up from below, and the flat floor of Plato is now 600 meters higher than the basalt fields of Mare Imbrium just south of it. And then notice on the western wall of Plato, that triangular chunk of the wall broke away, but it couldn't completely collapse and fall away because it's wedged in place by the basalt fill that paved over Plato. And then subsequent impacts, you can see at least 5 significant small craters on the floor of Plato. And if you have really good seeing, you can see up to about a dozen of these small little impacts on Plato. So again, crater formed by an impact, modified by volcanism, and then various other things happened throughout its lifetime to give it the personality that it has today. And moving on just south, the bird's nest form of Cassini crater. Similar situation. An impact back during the Imbrian epoch created a standard complex crater that had a central peak, had collapsed terrace walls, array structure, and then the Imbrian epoch volcanic flooding created Mare Imbrium, and the basalts crept up around lapped up to the edges of Cassini, and then, like Plato, volcanic eruptions from below the crater filled the interior of it with basalt. So we ended up with kind of a Plato look-alike, but then the subsequent impacts of Cassini A and B within its walls created this bird's nest appearance, bird nest with two eggs in it. And moving over to the northwest side of Mare Imbrium, the big horseshoe bay of Sinus Iridum, almost 250 kilometers in diameter. Now this follows the same pattern I mentioned with Fracastorius crater at the southern part of Mare Nectaris a little while ago. When this massive asteroid blasted this 250 kilometer diameter crater out of the rim of the Imbrium Basin, it had not yet flooded with these with the basalts that created Mare Imbrium itself. This was still a gigantic basin, so we ended up with a huge crater overlaying the rim of the basin. And consider that if this impact had occurred a little bit further west or a little bit further east and created a complete crater that did not fill in with basalt, it would be the largest crater on the near side of the moon. 250 kilometers. It would be number one on our side of the moon. But it formed on, again, the tilted edge of the Imbrium Basin. So the depressed inner wall, lower than the basalt flows that filled in Mare Imbrium, flowed over the rim of the Sinus Iridum crater, and then turned it into a horseshoe bay. And moving along, come on, giddy up, go. Down in the southern highlands, the elevated region of the moon that did not flood with basalt during the Imbrian epoch, we have crater on top of crater on top of crater. In this case, the major ones are in the center left, Stoeffler, center right, Maurolycus, and Stoeffler, a pre-nectarian feature. You see the inside of it completely filled in with debris thrown by the subsequent Nectarian epoch basin impacts that created the huge basin that now cradled the Maria. That debris had to go somewhere, and it dusted down all these pre-existing craters, completely buried the central peak of Stoeffler, and then subsequent impacts on its rim piled a crater on top of crater on top of crater. And see how the impacts created that unusual wave. Let's see if my cursor is working. This unusual ridge of material pushed over by the impacts that subsequently overlaid Stoeffler. And then moving over to Maurolycus, a Nectarian epoch impact, notice how its circular form overlaid a pre-existing crater here. Maurolycus overlays it, and down below, this rather significant sized crater protruding out from under Maurolycus. So a case of an impact modifying an impact, and then as with the case of Stoeffler over here, an impact modifying Stoeffler, another impact modifying that one, another one on top of it. So it just keeps on going. The last man arriving is the last one, first one on top. And alrighty, something has gone strange here. My advancing arrow is now covered by the screen share tool. I can't advance my slides. I don't know. Oh, there it goes. I can move. Oh, it moves. Okay. Learn something new.
There you go.
Alrighty. Yeah, continuing along the southern highlands, this particular grouping of craters down here. Whoops, I didn't mean to do that. This particular grouping of craters right here, this is Orontius, just a little bit to the northeast of Tycho crater, which is right here, just peeking into the edge. So gives you a perspective of where it is. But Orontius is another pre-Nectarian epoch crater. It's been there for over 4 billion years. And then during the Nectarian epoch, Huggins formed on its rim. And then during the Imbrium epoch, the Nezeredin, the next one up here, formed and overlaid them both. And then finally, during the Imbrium epoch, Miller overlaid them both. So we end up with something that kind of looks like a triple dip ice cream cone piled up on itself. Then finally, we'll take a look at the Aristarchus Plateau, way up in the northeast part of Oceanus Procellarum on the extreme northwestern part of the moon. This particular feature is a elevated volcanic plateau about 200 by 250 kilometers. And originally, it kind of stood alone, a raised, elevated area, highly volcanic. We see the little plateau wannabe here, about 40-kilometer diameter Herodotus, completely filled in with basalt. Just south of it, right where my cursor is circling, the volcanic pit of we call Cobra Head, that fed thousands of cubic yards of molten lava that flowed down Schroeder's Valley and emptied out onto Oceanus Procellarum. So this entire region built up by volcanism over a period of several billion years. And of course, at the same time, Oceanus Procellarum slowly flooding with basalt to become the largest of the Mare on the moon. But curiously, Oceanus Procellarum, so close to the western rim that it's very foreshortened to our view, and it doesn't even contribute to the caricature of the man in the moon. So it's just kind of rolled off to one side, and even though it's double the size of Mare Imbrium, the man in the moon's left eye, like I said, it doesn't even contribute to the face of the man in the moon. But as the basalts of Oceanus Procellarum got deeper and deeper, it flooded many craters like Prinz here, now turned into a small horseshoe bay in its own right, a ghost crater where only its rim is protruding. And then we leap forward almost 3 billion years to about, a 250 million years ago, and Aristarchus crater smashed into the southeast corner of the Aristarchus Plateau and excavated down about 3.5 kilometers. Blasted out a huge ray system that combines with the rays of Kepler crater and Copernicus Kepler to create a white spot on the moon that we can see with the naked eye at full moon. So just a little march through time, seeing how the different features on the moon evolved over literally a period of billions of years throughout the successive epochs of lunar time. So the moon is not static by any means. It's been a constantly evolving body, and it changes night by night as the phases advance, the shadows change. It presents a new face to us every night when we go out. So I encourage people to go out and look at the moon, study it closely. Of course, buy my book to get fully educated on the moon. Then you know exactly what you're looking at. It's a world waiting for you to enjoy and relish from your own backyard without having to go out to dark skies. So I will close with my standard slide, which shows there is much to love on the moon, and I invite you to come out and play with me on my lunar playground. So
Wonderful. Thank you.
You bet.
More incredible images. I never get tired of of seeing your work, Robert. It's
Chelsea
incredible.
Bondswall, watch out.
Well, if you like what you see, like I said,
Yeah, those are beautiful, really crisp and sharp, high resolution.
thank you.
Just
And,
A lot of lot
yeah,
of shots to get those perfect like that, huh? How many?
well, of the library of about 2,000 of them that I have, I've probably thrown away 10,000 trying to
Oh man,
wait for the right moment where the sky is.
micro.
Yeah, takes a while to wait for the scene to settle down. So
Great.
it's
Probably
been fun.
better with a smaller, like trying to do that with a 28 might be futile, right?
Well, you got a point. Many of these were taken with a 7-inch Maksudov, an 8-inch Celestron, an 11-inch Celestron. When I use my 14-inch Celestron, the seeing starts to get to me, and the
Yeah.
lunar images through the 14 are actually worse than the
Mhm.
smaller telescopes. Now, that said, during a period of extraordinary seeing a couple of summers ago, I got some of the best images that I have of the moon taken through a 20-inch Dobsonian.
Wow.
So it's the pure luck of the draw with the seeing, but the
Mhm.
smaller telescope will tolerate bad seeing better. So
That's true.
that's
And you
my
can
story,
always
and I'm
stop
sticking
down
to
a
it.
bigger telescope with using mass. You know,
Yeah,
of course, you can't go
this is
the other way around. But
They say
yeah,
the
that is true.
telescope that you use the most is your best one, and I would say the smaller ones are probably more usable on more nights just due to the weather. You know,
Yeah.
the
Well, for high resolution work, yes. Now,
sure.
when I'm using my Hyperstar on the Celestron 14, it doesn't care about the seeing because the focal length is
Right.
only 600 millimeters. So
Wow.
each has its
Mhm.
particular niche where it works
Mhm.
best.
Mhm.
So I enjoy them all. Have a telescope for every day of the week now.
Yeah, Robert, when I mentioned stopping down a telescope, I noticed that you had some reservation about that. What do you know? I mean,
Oh,
you are
well,
really one of the great high
it's a
resolution imagers out there.
well,
So
it may I should try that with a 14. My if I sounded like I had a reservation, I was thinking of the 20th Dobsonian and
I
just
see.
wrestling that monster out of the garage. I mean, it's
Yeah.
That's
You know,
true.
I did the 28 and I was getting some good views when I put that off aperture mask. I had an unobstructed like 10-inch telescope at like an f15 or something, and it did damage. It showed some white clouds that we couldn't see, and I had a friend there with a really nice OGS 16-inch classical Cassegrain, a carbon fiber with all the bells and whistles. And the image in that Cassegrain was really amazing. So sharp. It was, great seeing. And even the stop down version was showing those white clouds a little better than he was in a panic trying to get them, but eventually he got that thing acclimated. And what a night, what a night of visual astronomy on the planets.
Those stick with us.
Mm-hmm.
Thank you, Robert. Thank
You
you.
bet.
Thanks, Robert.
Okay.
Okay.
Later.
All right. So, John, you are out there in the cosmos. I can see your,
Yes,
the Milky Way behind you and sky filled with stars. It's beautiful. It's beautiful. It's been a little while since you've been on, and so
yes.
we're happy to have you back, of course. And what do you have to share with us this evening?
Well, I'm always under the stars, and especially in the daytime, I sweat a lot. But that's because I'm under the brightest star.
Yeah, that's right. That one that's so close. That's right.
But I try to get the morning sunlight. Then I got to cover up because it's so intense. Even at 98 million miles, it still burns me like bad. Like literally, I can't even pick up like a tool. Sometimes it's so hot. It's just unbelievable.
Oh yeah.
But I'm in the Milky Way because this is where I love to be, is under the stars, looking up and cooling down a little bit with that nice cool light from the night. It's always comfortable when the temperature fades down. I've missed a lot. I know the big eclipse was just amazing for those who had the fortunate clear sky, because a lot of people didn't have that. You know, a lot of clouds were affecting most people. So I actually didn't go on the trip. I decided, you know, I'm going to stay back and try to do something here. And it's a good thing I've got friends in high places, because all those friends that had the clear totality, I was able to utilize their views to get a little something for my presentation. So tonight's presentation, I'm going to go into a little bit of the eclipse, because that's a stellar event that we had, and a rare event that a lot of us missed. So I've got some amazing pictures from amazing friends that were so kind to give to me. And then also I'm going to do a presentation on my drawings of the springtime galaxies. You know, the way I see things, I have my own vision. This is a self-portrait I did. It's my profile page. It just shows me focusing on that color and the light, you know, the vision of this beautiful hobby, and all the amazing colors and different vistas that we can see. And that's what my self-portrait represents. So, you know, again, if you ever want to check for an eclipse, you know, if you look at the trees and you see these weird crescents, you're not seeing the moon. You're seeing the sun with the moon in front of it. And that's a real indicator that we're having an eclipse. And, you know, twice it's happened. I didn't know we were having an annular. And then all of a sudden I said, oh my gosh, we're having one. I got to get home quick. So that's I call that the handmade camera obscura, you know, like the old days. It's just a pinhole camera.
Yes.
So this was the annular eclipse from before. This was something I created once I realized I ran home. And I just worked off a cell phone snapshot, and then I painted the clouds from scratch, because I love to paint clouds. It's one of my favorite things, you know, galactic clouds, galaxy clouds, nebula clouds, clouds. I mean, clouds are amazing. This was a friend shot of the annular eclipse. They had went to New Mexico, and they projected this image onto their hand. I thought it was really cool. And I'd like to share this with everybody.
Yeah, that is cool.
If you remember the last time I went on, you could see, you know, what I was doing. I was projecting the moon onto that piece of paper, which was also really cool. So, you know, projection is a good way for the bright objects, especially the sun, because it's safe. It won't fry your eyes. Don't look at that. Just shine it onto something. So now this was one of my friends from Dallas. It opened up. I called him. I said, hey, it's about to hit. It's coming your way. We were in Kerrville. I wasn't. My friends were. That's where I was going to go. And he sent me this picture. So I had this to go to work. So now I went to work and I created this from that. This is digital painting again. Yeah. This is all on my cell phone at this point. Then I go to Procreate and bam, there it is. The clouds parting, and lo and behold, totality. So that was my piece I created from that shot of the eclipse. And those clouds are hand painted clouds, by the way. You look at those.
Wow.
Those were done with the cloud brush in Procreate, and there's another brush that I use. But yeah, not bad. And, you know, I created this because I wanted to share this with all the people. There were probably $7 million or $1 billion spent, and a lot of people didn't get their money's worth. You know, you did okay at your event?
Yes, we did. We got very lucky.
Oh, wow.
With the clouds thinning just enough for us to see totality and to actually see the corona. So it was only about 30 seconds, but I can tell you that we were all not only relieved, but elated. It felt like some sort of rebirth experience or something. It was cool.
Man, I've got to get hatched again. I'm thinking maybe the next one in Australia, but we'll see. This was a beautiful diamond ring. So after the eclipse goes through totality, this is what's called the diamond ring. Again, the clouds were threatening. This was another friend, and this is another cell phone snapshot, if you can believe it. The diamond ring.
Yeah.
You know, if I saw that with the wife, I'd have to get her another ring, get remarried on the spot, because that's a beautiful, beautiful thing to
That might
see.
be worth it.
Now we're getting into the local neighborhood. So we're back. I stayed here and I had friends that we were all on the phone, you know, sending pictures back and forth. And so this was one friend's white light. You know, I think it was with a Bader style film, the Mylar Astro Bader film.
Mm-hmm.
And then this was my friend Chris. So what he was doing was sending me images, and I would process them differently with my meager free program, Photoshop Express, and also my dedicated Samsung photo editor, and I could get different effects. So this effect was to get the prominence coming out. You see them on the limb, those little prominences?
Yeah.
So that gave me the edge detail in that particular processing. Now, this is not even real Photoshop. This is just Photoshop Express, a free program, unbelievable program with their filters and all their levels tools, you know, contrast, clarity, texture, shadows, black, white, highlights, warmth, tint, vibrance. There's many different settings. Now I went to the surface, you see, to get the granularity and the focula. So you have more of the surface detail now. It's almost like having a digital pressure tuner or a tilt tuner, you know? So I'm getting a different effect with his shots. Sending them back to him, he was elated. Now this one is a friend of a friend. This is actually, if you've heard of Dankmeyer binocular viewers, Russ Dankmeyer, this is his shot. He's built this scope and made his own Etalon, and this is his live view of this prominence. This was a few days before the eclipse. And is that not amazing, the size of that prominence?
Oh, yeah.
If that was pointed at the Earth, we could be in trouble. I saw the same prominence with my first light on my new 50 millimeter Lunt pressure tuned. Unfortunately, I was so elated when I saw that I went to move it down a little bit because it wasn't tracking, and I had it in this cheap tripod. I really should get one of those from you, the one with the dual saddles. What's the name of that one?
You're talking about the Twilight 2.
Yeah, the Twilight 2.
That particular mount's no longer available. It's out of production now. Yeah.
Well, maybe I'll find one used, but I definitely need something sturdier. My scope actually fell out. I barely caught it. It dented, so I had to have it worked on, but I caught that prominence. That was from memory because I only got a little look, but it's pretty close. Not bad for my first solar sketch.
Yeah.
Now we're getting into some of the later, night, late in the evening, about 2 to 4 o'clock. If you could stay up that late, you'll get to see the highlight nebulas again. Early on, you can see the Lion Nebula, which is the Eskimo. This happens to be the Dumbbell Nebula that I sketched. And this is a new version that I've been working on, adding details from this year because I've had a chance to sit down and really study it. There's the Lion Nebula, also known as the Eskimo. Now, these are all out in the course of a night right now. This is early in the evening because Gemini's starting to go towards the horizon. So it's, you've got a few more weeks, maybe a month or two max, and it's gone. Now, this one is something I've really been working on. I'm very, very excited to show this for the first time. My newest ring nebula. So if you look, I've been seeing the central star the last couple times I got out, and the second star. So those were with a 32-inch and a 28-inch telescope to be able to do that. But I mean, I think I've captured the essence of that.
That's what it looks like visually. It looks nice.
It's floating almost, isn't it?
Yeah.
I hope it portrays the same on the on your screen. On mine, I'm almost like I'm there. It is just amazing, the digital, what you can do with it. And again, I use that 9mm 120, and that's my view with that thing, that huge That is a big eyepiece. And it gives you the big view and the big Dob. I'll tell you, if you have a Dob, it's a must-have, especially if you're up in the 20-inch range, even 18 or 16. That eyepiece it opens up the field and it brings you close. It's just spectacular view, man. Thank you for that one. Okay, so now we're going to go to the springtime galaxies. These are out. This one's early, Leo, M91. M64, the black eye. That's another great one to look at in any scope right now. That's in what? Como Berenices, right? I think the constellation.
I see.
Near
Beautiful
not
drawing.
Hector. What is that star? The red star that marks that constellation. I'll think of it in a second. Aldebaran. This is again the sombrero. And this is very much what it looks like in my eyepiece, the color and everything. I mean, that is just hard to believe when you see that in your eyepiece, that it's actually real. Happy Cinco de Mayo, everybody, by the way. Belated. My whale. So this, I used the Malincam image from Riverside, and I added the color and some more of the spectacular starburst. It's like M82. That X in the middle is just exploding from the activity in the black hole, and it's creating all this illumination from the core. Just an absolute spectacular thing to see on the screen. So I've combined a sketch with the data that I was able to obtain in the color and some added details from the Malincam. You see the clouds on the right of the galaxy. There's like clouds. It's pretty amazing that nature is reproduced here on Earth,
Yeah.
Just like a galaxy clouds. It's really amazing. Macro clouds almost. And that's a companion right next to it. This is my newest redo of NGC 4565. It's an Edge-on galaxy. It looks like that B2 or the B1 bomber that we made, the wing, coming in for a landing. But this is a showpiece summertime galaxy, edge to edge. I did a couple renditions of this. This is the angular version, and this is the coming in straight across the horizontal. I'm not sure which one I like better. Look at the detail in that, though, Scott. Those spires coming off of there,
Yeah.
they're light years
Like
above
in
the
the
disc.
in the dust lane there, you can see like these vertical.
Right. And, just
protuberances.
like our Milky
Yeah.
Way.
Yes.
If you look in my background, like the horse, they have the little pony, and that's exactly what those are spires. And our galaxy has two super bubbles on the north and southern pole of the, top and bottom of our galaxy. I'm very proud of that one. Really love it.
Oh, yeah.
Kind of flying in. Isn't that amazing that that's out there?
Mm-hmm.
It's just mind-blowing. So what this is representing is, say, if you looked at our Milky Way galaxy from how many 40 or 50 light years away, you would see ours, if you're looking from the side, like a plate sideways. But then when you go to M51, you're looking down on it. So it's all about orientation, which dictates what type of galaxy you're looking on. Either a grand spiral, slightly tilted edge on, like M106, 108, or you could have your edge ons like NGC 5907 and Draco, and the needle, and then you could have that one. So it's all where we're orientated in space and how we're seeing these galaxies as they're all moving in different directions. This was the other day when I was walking my dog. I just looked up and I saw this, view, which, once again, if you're not out there looking up and always, keying in on these beautiful things that are happening every day all around you, you'll miss these things. But I was fortunate to see this. And it started my day amazing and finished my day amazing. That was the end of the day. The clouds had parted. There was a little rainbow and a dove flying in the field of view. Just, man, what a great day to be alive and to experience the beauty and see these wonderful things that we're all so lucky to see, you know?
Right?
And you can't forget about the rainbows. You know, raindrops are falling on my head sometimes, but when you look up, guess what you see? Amazing rainbows.
Amazing. Amazing.
And it just gives you hope, and it tells you there's a lot ahead of you that's going to be amazing. So you got to look up, you got to get equipment, you got to look and get out there, because this stuff's all around you. Look at the colors. I mean, where do you see this? I mean, this is the most amazing, you know, thing to see, and it's just
Planet
right
Earth
here.
is beautiful in so many aspects, you know. So,
Yes,
yeah,
man.
when you
What?
think
And
that you're having a bad day, you know, you just
Mhm.
got to settle back and look at, you know, breathe deep, because
Oh, that's what I was going to say. When I saw this rainbow,
yeah,
I breathed through my nose slow and deep, and I inhaled the wonderful air, clean air, and I exhaled all the trouble, and just,
there you go.
it's gone, man.
Yeah,
There's nothing that can bring you down when you just have the gift and the realization, and you see this, and it's magic, man. This life is a gift. So grateful.
agreed. Agreed.
I created this one.
Mhm.
This is an artistic kind of a little different approach to the Trifid Nebula. You know, Van Gogh was affected by the first plates that were done, the astronomical plates. You know, Starry Night might have been his interpretation of looking at some of these plates. But this was looking through my 28, and I had a picture to work with that Mirko took, and the colors are very reminiscent. It's an abstract version of the Trifid Nebula. Can you see the central core part, Scott?
Mhm.
The dust
Yes.
lane, that's that
Oh,
X,
yeah.
and then that
Yes.
little
Right. And this kind
pillar
of
with the
white
little spire coming out. Yeah,
star. Yes.
but
Sure.
it's just something I thought was cool. And, you know, just taking a different look at what God's created and the creator's created, you know, I guess it's the creator, is who you would say, or the universe. The universe is amazing. I mean, look at the flowers. This is just walking the dog. This is actually a piece I created.
Mm-hmm.
Different look, but again, you know, stopping. There'll be days when I smell the roses, that's for sure. People drive by and look at me strange, but you know what? I'm taking that rose in. I'm getting not only the smell, but the vision too. It's
Oh, sure.
dimensional. This
Yeah.
is another one, the beautiful opposite on the color wheel, pink and green, you know,
Mhm.
orange and blue, red and green. So it's kind of a cool, you know, difference, gives it a nice contrast, beautiful flowers. Again, appreciating the creator's gifts. And there's the rose. Boy, I went up to this rose and I just took a big breath through my nose, and the lady just looked at me funny. And then I said, "Oh, that's a beautiful rose." And she smiled. I love it, man. You know,
Yeah, what?
it's
They
funny.
never saw anybody smell a flower before? Come on. Come
They
on.
probably thought I was a little feminine, but hey, I am sensitive. Let's just say,
Okay.
yeah, when you have a heart, you're sensitive, right?
That's right. That's right.
Of course, I have to always close with my little friend. He was a little worried about me right here. I
Hmm.
was, you know, talking about astronomy, and he's like, "Really? Can't you pay some attention to me?" And then I said, "Sure, let's go on a walk." And he gazed off. He goes, "We're going on a walk.
Yeah.
We're going to see the flowers and smell the sky." And, you know, he waters the trees. He's a good boy. He's my
Yeah.
buddy,
Yeah. Oh,
my
yeah.
little Bosco. And, you know, it's always good to have that observing partner. So when I was sketching this one, he was waiting. saying, "Come on, man, can we go to bed now, please?" I go, "Yes. Let me just finish this cloud and we'll go."
Yeah.
So that was my night, and there's my presentation.
Thank you, John. Thank you, man.
You're welcome.
All right.
Thanks, everybody. I hope you enjoyed it. It's great to be back.
We'll see you next time. Okay.
Yes, sir.
All right.
All right, Scott. Have a good evening. Thank you so
Okay.
much for having
Thank
me.
you.
Bye-bye.
Thank you. All right. So we are to our final presentation with Marcello Souza. Marcello, it's great to have you on Global Star Party. This is our, can you believe it? This is our 149th Global Star Party. We have, I don't know. I mean, I think the average Global Star Party runs about 3 hours or so. Some of them have gone all day. We had one that ran 24 hours. We've had others that are 5 or 6 hours. But let's count just 3. That's quite a bit of programming and so much information from the presenters, including yourself. So I really appreciate this because I know that you've done probably way over 100 global star parties yourself. So yeah, so you've been with us through thick and thin on all of this. So I really appreciate it. I really appreciate it.
It ever is a great pleasure and congratulations, Scott, because
Yeah.
to be
Next one is 150, and then we'll do that next Tuesday. So yeah,
you need to make a big celebration because it's fantastic to have 150 programs, no? But
yeah.
began
Thank you
during
so
the
much.
pandemic periods, no?
Yes.
And I was talking about this here because many things changed
Hmm?
after the pandemic. During the pandemic,
Oh, that's true.
and you have this until today. Né? We found new ways, né, to have contact with people, and
Yes,
then
yes. And we all made many friends around the world on
yes,
this platform. So, and that's true for us that are presenting, and then, of course, our audience as well. They became familiar with each other. So it's been a lot of fun. So, and I think we have one of the best audiences out there. So thank you so much for all of you that tune in. And I'm going to give you the stage, Marcello. Thank you.
thank you, thank you for the invitation, Scott.
Yeah.
Ever is a great pleasure to be here. I will talk about basic physics today. Né? It's something that is associated with astronomy, but is basic physics. Né? I will share my screen because it's something that ever when we organize an event that people ask. I will talk about the special relativity, and I don't know if you can see here my
Einstein.
presentation.
Yes.
Yes,
A
I'll
young
talk about
Einstein.
yes. In the periods that the published the most important papers, that one of them was about the special relativity. Uh, this in 1905 is we call the annus mirabilis, the same that we use for Newton, né, during the period that he produced the Principia. And this year, in 1905, he published 5 articles, but 4 of these articles were fantastic. The first one was published in March 17, that is about the photoelectric effect, that is on a heuristic point of view concerning generation and transformation of light. That is the photoelectric effect that he explained the results, and is the base of the quantum physics, that you have light as a particle and electromagnetic wave. And we use until today, this in the streets, have many sensors that are produced with this article. This was his PhD thesis, that's on a new determination of molecular dimensions in April 30. But what is fantastic is because he tried before to get a PhD title, but he was refused by the university, and he had to, years later, he produced again a new project, a new work about the same topic, and he received the PhD. That's fantastic. Who can imagine a person that work in an office and he was nobody would like him to have him in university, has his PhD refused, and then in 1905 he produced the articles that changed our life. And have another one that's the Brownian movement, that's on the motion of particles suspended in fluids at rest, as postulated by the molecular theory of heat in May 11. That's another topic of physics. And then in June 30, it is the first article about the special relativity, that's on the electrodynamics of moving bodies, that is the base of the mechanics of the cinematics of special theory of relativity, reproduced in June. You see, you have different topics. Each of these topics, he will receive the Nobel Prize. He received Nobel Prize was not for the special theory of relativity, but was about the photoelectric effect, the first paper he published this year. And in September 27, he published another article about the dynamics, the relativity of relativity, and it is in the article that appeared the famous equation, variation of the energy is equal mc squared. And why I'm talking about this, I'm talking a little about the special relativity. The problem, the question is this: what is light? This was the problem that you didn't have an explanation, an exact explanation at the end of the 9th and the beginning of the 20th century. Right? Is it a electromagnetic wave? And if it is an electromagnetic wave, how do they propagate? Because the problem is everybody was trying to reduce everything to the mechanics. And it is a wave, is a transversal wave, like you have a mechanical wave. But the problem is that a mechanical wave needs a medium to propagate. And the light propagates in vacuum. Then what they were trying to find is a medium where the light propagates. Then, is it a mechanical wave? The equation is the same of the mechanical waves that if you from the Maxwell's equation, it's possible you have condition to write a wave equation like a mechanical waves for the electromagnetic waves. But you need to find a medium to propagate because propagates in vacuum and the mechanical waves propagates in the medium. And then they imagine probably that you have a medium, but we don't know. They didn't know what was this medium. Then they imagine that was something that is around the Earth, but we can't measure this medium. And they call something that's coming from the heavens, that's ether. And how that we can have a theory about something that you don't know what is. Then what they imagined, they had many ideas. They thought that maybe the Earth is rotating, and this medium, the ether, is rotating with the Earth. Then if you measure the light velocity in one direction, it will be different if you measure in another direction. Then they try to measure the velocity of the light in different directions from here on the Earth. The most famous experiment is this, the experiment made of Mixon and Morley. They measured the velocity of light in different directions, and what they have as a result is this, that it is impossible through any physical experiment to detect the movement of the Earth in relation to the ether. Then, if the ether exists, we don't know because we can't measure. We don't have any experiments that show us that this medium exists. This was the problem at the end of the 9th century and the beginning of 20th century. Then arrived Einstein. What they did, they postulate that the light always in vacuum propagates in vacuum with a constant speed c, independent of the state of motion of the emitting bodies. This is something fantastic because he published an article that begins with postulates that something that you don't need to prove, and they accept this article. And the other is that the laws of physics are the same in our inertial systems. Inertial systems are systems that moving with constant velocity. Then there is no privileged inertial system. Before he published this was only possible, they consider only this for the mechanics, now for all the physics. And the first postulate is something fantastic that changed our idea of space and time. Why this changed our idea of space and time? Now I am trying to make to show in a simple way, for who don't. You have here a frame. You have here a system that is moving, and a person here that is not moving, because also the referential is relative. But we will consider that the car is moving, you have someone looking this car moving. Then you have the car moving with a velocity v. This is a referential that's moving relative to the person that's here. And we know from Galileo that if you are in a car and you don't consider the wind, if you have a ball in your hands and you move the balls up, then they goes up and come to your hands because it's moving with the same velocity of the car. But if you are outside the car, you see the car moving and the ball doing these movements. There's a parabolic movement. And then what you see, the movement that you see, depends on your referential, the reference that you have. And also, something that's important for us is the time. Because in our words, if you, as a simple example is this, you are a movie theater here, and you invited someone to see a movie. But it's not enough you say what is the movie theater that you are going to see the movie. You need to say also at what time you are going to see the movie.
Yeah.
Then an event in our words, you need to say the three coordinates of space, and also you need to say the coordinate, the time. Then you have a word that consider the space-time. You have space and time that you need to have an event defined. né? Then this is something that, but before Einstein, we imagine that the time is the same for everybody. Your measure, when you measure the time, I measure the same time here. No? They, but I will show that Einstein changed this. This is something fantastic that we can't see, you can't imagine our world with 4 dimensions, if you consider the space and the time. But if we reduce one of the coordinates of space, we can imagine this. Like we take many pictures and put all the pictures that evolve with time, one up the other, like this. And now you see the movement of the ball that leaves the hands of the girl, goes to the wall, hits the walls, and come back for her. This is the evolution in time of the movement of the ball. Then we are considering 3 coordinates, 2 of spaces and 1 of the time, the evolution in time of this movement of the ball. And something that we know, that's important of the reference that you have from where that you analyze the movement is this example. Imagine that you are in a shopping center and someone is in this is the stair that moves. I forgot the name in English that you use for this. A stair that is moving. And then you are moving down in a stair that's moving up at the same velocity. Then for this person that's here, B, you are not moving because you are moving same velocity that the star is moving up. But for the other person that is not moving relative to the star, he is moving for the person that's there outside. Then he will say that the person that is not moving relative to the star is moving, and the other guy that is moving relative to the star is not moving. Then it depends what you see, depends where you are, and how is the relation of the movement associated to you for your position. Have many examples like this. A bicycle, if you are moving with the person that's on a bike, with some lights, when he is moving, if you are moving with him, you see this circle. If you are outside and the bike is crossing you, you see this. That is a cycloid. And now I will try to reduce this and consider the postulates of Einstein. The first postulate. Here you have a train, and you have a person here in the train. The reference here, referential here is S line S with this line here. And you have someone outside that the referential is S. And the train is moving with a constant velocity relative to this person that is here, the referential S. Then who is inside the train is moving with a velocity V relative to the guy that is outside the train. Now you have 2 referential. One, that's the person outside, and one is the person inside the train. Now, I will try to show you that if you consider the Einstein postulate, the time will be, the interval of time will be different from the person that's inside the train from the guy that's outside the train. You see here, you have here a light in the bottom here of the train, and the light moves to a mirror that is here near the floor. Then the light goes up and come back. This for the person that's inside the train. But what see the person that's outside the train? If he can see these lights here inside the train, he sees the lights going up, but the train is moving with a constant velocity. Then the light do this movement that is represented here by the axis. Then this is the distance for him that light travels to hit the mirror that's here near the floor. Then what we see? For the guy that's inside the train, the light travels from the bottom to the top, and the distance is L. For the guy that is outside, the light's movement is from the bottom to the top. Here is axis. Axis here is a triangle with an angle of 90 degrees. Then we use the Pythagoras formula. And then what you see, the time that the guy that's inside the train measure, the interval of time for the light to move from the bottom to the top is the distance divided by c, that is velocity of the light. Before Einstein, the velocity of an object, and for us, they changed because you have to consider the velocity of the referential. But for light, this didn't happen. This don't happen. They don't consider this. They consider that light will move with the same velocity for the person that's inside the train and for the person that's outside the train. Then the person outside the train, for them, the light is moving with the same velocity c. But the distance is bigger, is this axis. Then when you divide x by c, you have a different time. That then the guy here measure one interval of time for the movement of the light until hits the mirror, and for the guy that's inside the train, he measured another interval of time for the movement for the light until reach the mirror. Then the time is different from both. Before Einstein, they measure the same time. They measure that they will measure the same time. But for the postulate of Einstein, as the velocity of the light in vacuum will be the same for both, then the distance will be different, then the interval of time will be different for them. Então diz, the distance is different, then the interval of time is different. And you can use here the Pythagoras formula to associate x with L, and then if you do this is a simple way to imagine this idea. You have to use a different mathematics to have a precise solution, but doing this, we have this equation, the relation between what measure the guy that is outside and what measures the guy that's inside the system that's moving. And you see that below here, you have an equation that you have 1 minus v squared divided by c squared. And what this produce? This is a number that is very small because the velocity in our words is very small if we consider relative to the velocity of the light in vacuum. But then if you are moving very fast in a velocity that is almost near the velocity of the light in vacuum, this number is important. And then you have difference of time. They measure different times. In our words that are very small, the velocity is very difficult to see this happen here in our words. Then only for big velocities that is possible to measure this. Then the time is different from two different Excellent. And they measure the space contraction. The space also, the person that's moving fast, they see the space moving direction of him, and then they measure that space is contract. And the other fantastic result that I'll not talk about this to show how that we arrive in this equation, but is that the relativistic mass, the mass of the object also change with the velocity, how that the object is moving. And this is important because this shows that we can't reach the velocity of the light in vacuum. It is a limit for us. How this happens? If you look here, if you have the velocity v equal to c, then you have c squared divided by c squared. That the result is 1. 1 minus 1 is 0. And a number that is divided to 0 goes to infinity. Then the mass of an object goes to infinity. That is you don't is a you have no limits for this, né? When you try to reach the velocity of the light in vacuum, then it's impossible because you need an infinite energy to reach this velocity. Then it's impossible for us to reach the velocity of the light in vacuum. Then our world will move below this velocity. And as the velocity of light is constant in vacuum, is a way that we have to know the distance of objects from us. Né? Then you know, you measure the time, you have an object very far from us, and you can know the distance from the time that the light needs to travel from this object to us. This is a reference to us. Then when we look to the space, we are looking to things that happened in the past. Né? Then the light of the sun needs almost 8 minutes to reach us, approximately. It's a medium, a medium. And when we look for the star that if not consider the sun, the other star that's closest to Earth, the Higgle Centaurus, Alpha Centaurus, but is almost 4.3 years. That is the time that the light needs to travel to reach us. Then we are look to the past. And also we know that the result of one of the use of the theory developed by Einstein was the production of atomic bombs, unfortunately, but it's the same energy, the same process that you have the interior of the stars that is responsible for us here to send energy to Earth, from the sun. Né? You have nuclear reactions in the core of the sun. I know that is a topic that have many examples and many different. Needs a long presentation. I tried to talk in a short presentation about some aspects of the special theory of relativity. Thank you very much, Scott.
Well, I appreciate that. I appreciate that. Who better to who has studied time more than Einstein? So, yeah, very good.
He changed the word.
Okay, well, I want to thank you very much for coming on, Marcello, and I hope to see you next week on the 150th event. It will be on the 14th, starting at 6 p.m. Central, and I'm really excited to get that underway. So, still quite not quite decided on the theme. So, but it's a special time for us. So You guys have a great night. And what time is it in Brazil right now, Marcelo?
Now it's midnight.
Midnight. Okay.
Midnight and 3 minutes. I think that you are in a different time zone now.
We're in a different time zone. That's right.
I changed your time zone, I think, no?
Yes. All right.
Uh,
Well, have a good night, Marcello. Thanks very much.
my
Thank you.
pleasure. Good night.
Okay, and I want to thank the audience for tuning in. I have a couple of videos that I wanted to share with you before we close the night, but you know, we really want to thank our audience that has watched us for, you know, so many times. Perhaps some of you remember the early days of Global Star Party, and it's been a real pleasure to put it on, and I look forward to it each week that I can do it. So, but these are some videos. I am a NASA Solar System Ambassador, and I love to do outreach, and I love the outreach that NASA does as well, and the European Space Agency as well. They both of these organizations do a tremendous amount of work keeping the public interested and to explain some of the more difficult concepts that it takes a bit to get your head wrapped around in astronomy. So, but this is a segment about Hubble, and you know, Hubble also works off of clocks and time. So here we go.
Remember that Y2K thing a few years ago, where everyone was afraid the world was going to end because computer programmers saved space by putting dates as 77 for 1977, 85 for 1985, or 90 for 1990? But then it became clear that when the year 2000 finally rolled around, all of the computers would think it was actually 00, or the year 1900. Well, it turns out Hubble has something similar. Only Hubble's clock restarts every 6,213 days, 18 hours, 48 minutes, and 31.875 seconds, or roughly every 17 years for those of you who like counting. That's because Hubble's computers have a different way of tracking time than we have here on the ground. You'd think it would be as simple as syncing our ground clocks with Hubble's personal timepiece, but you'd be surprised. Hubble's onboard clock is a 32-bit elapsed time counter. So instead of Hubble counting up seconds, days, months, and years like a calendar as we know it, Hubble counts every 125 milliseconds, or 1/8 of a second for those of you who like counting. Using 32 bits, up to 4,294,967,295 increments can be stored. Once that final bit is hit, however, everything restarts again from the top. So to clarify, when Hubble was first deployed on April 24, 1990, its clock began counting up every 1/8 of a second from April 24, 1990. And for every one of those 1/8 of a second, Hubble's binary counter got one step closer to its maximum of 4,294,967,295 before restarting back to 0. This actually happened already. Hubble had its first clock rollover back on April 29, 2007. So from 1990 to 2007 is 17 years, and then from 2007 to 2024 is another 17 years. So this will be Hubble's second clock rollover. When you do the math, 4,294,967,295 multiplied by 0.125, or 1/8 of a second, divided by 60 seconds, divided by 60 minutes, divided by 24 hours equals 6,213.78 days. Our magic number of around 17 years. That's all because Hubble's initial requirements back when it was being designed and built in the 1970s and 80s specified a base mission period of 10 years with a 15-year operational goal. Therefore, the 32-bit clock design with rollovers every 17 years met those requirements. But why does this even matter? Why not just let the numbers roll over on their own every 17 years and start things from the top again? Well, if we tried that, things would get pretty weird. That's because Hubble would suddenly think it was 17 years younger. It would think it was back at that first clock rollover we just talked about that happened on April 29, 2007. If Hubble thought it was 17 years ago, it would be very confusing. Hubble's antennas would point in the wrong direction when trying to send data or receive commands from a communication satellite that was somewhere else. Because Hubble would think everything in space was in the same place it was 17 years prior, Hubble would even think it was in a different place. And even more dangerous, Hubble would think that the sun was in a different place. And if Hubble looks at the sun, that could be very, very bad for its delicate instruments. The fact that the second clock rollover 34 years after Hubble's initial deployment is now upon us is yet another testament to the dedication and ingenuity of everyone who built, upgraded, and continues to maintain Hubble as the premier astronomical observatory we have come to know and love. Back before the new millennium, computer engineers around the world updated things to have all 4 numbers of the year instead of just the last 2. So we managed to keep that Y2K bug from actually destroying everything. And just like we managed to avoid any mishaps with that issue, our team of Hubble engineers on the ground have sent up new routines to ensure that our trusty space telescope could successfully roll over its clock without dropping back 17 years. That way Hubble can keep doing its amazing work until the next clock rollover in 2041.
Good day, everyone. This is David Levy, that's me, and I am holding the original Discovery films of our most important comet, Comet Shoemaker-Levy 9. These films were taken on the 23rd of March, 1993. Carolyn discovered the comet on these films 2 days later. And about 16 months after that, all of the fragments of this comet collided with Jupiter, giving humanity its first view of what happens when a comet hits a planet. And one of the exciting things about this is that when comets hit planets, they don't just drop dust. They also drop organic materials, carbon, hydrogen, oxygen, and nitrogen, which eventually turn into proteins, amino acids, RNA, and finally, on one magic day, DNA. Comet impacts are really the first step in the origin of life. I'd like to invite all of you to come to the next Global Star Party. They are run by Scott Roberts of Explore Scientific and me. We co-host this program, and it's usually done on Tuesdays, and usually at 6 o'clock or so Central Time. And so I hope to see you all there. My name is David Levy, and I hope to see you all at the very next Global Star Party. Thank you.
Mm-hmm.